So welcome everyone to the second day of the AFLOW School hosted by Texas A&M. As a reminder, I would encourage everyone to log into the video portal since we're going to be starting with some exercises and demonstrations fairly quickly in this first session. So please go ahead and log into that. And while people are doing that, just a recap of what we did yesterday. So we did a brief command line primer, an introduction to AFLOW, and then Dr. Koriosis gave you an overview of DFT and VAST. And then at the end of the day, I showed you how you can use AFLOW to accelerate and automate some of these DFT calculations. So today, for day two, for the first two parts, for session 3, we're going to have a symmetry session. So we're going to be talking about how you can use the AFLOW symmetry software to characterize your input structures and the relaxed structures. And then after that, after lunch, we'll be doing a section on structure prototyping. So this goes back to the idea of creating these geometry files from the command line. And we'll show you some of the different formats, different ways you can construct geometry files. And then at the end of the day, Dr. Marco Esters is going to be talking about the AFLOW database and the APIs. Okay, so if you'd like to follow along, so there should be a day 2 folder. So if you go to your desktop, you should see day 2. And then we're going to be starting with the symmetry. So if you do CD03 symmetry, and you can see we have the exercises, and then we also have the PDF of the slides if you'd like to follow along as I'm going through the first part. Okay, so I guess we'll go ahead and get started. Sorry, 1 second. Let me change the presenter mode so it's a little larger. There we go. There we go. Hopefully everyone can see a little bit better. Okay, and again, feel free if you have any questions during this first part. I'm going to be giving an introduction. So if you have any questions about some of the theory or the things that we're doing, feel free to post in the chat or raise your hand and unmute yourself, and I'd be happy to take questions as we're going. So, okay, so as a reminder, I don't know if I introduced myself. My name is David Hicks. I'm a postdoc at the Center for Autonomous Materials Design. And so in this third session, we're going to be talking about AFLOW-SYM. It's a symmetry package that we've developed in the group to calculate the crystallographic symmetries of crystals. And so just a brief motivation for this. A brief motivation for this is, if you remember from the previous sessions when we were talking about modeling with DFT, really the only input that we had minus some pseudopotential information and parameters, really the base of it was the underlying structure. And so this is kind of getting to the idea of the structure property relationship. So if you have a particular geometry, and basically we want to determine its properties. And this is basically the foundation of materials modeling. And so one of the goals here is we want to better understand the structure. And one of the ways that we can do that is by classifying its symmetry. And so one classic example of this structure property relationship is symmetry versus piezoelectricity. So if you're familiar with the phenomenon, when you apply a force to a material, you might observe voltage across the material as well. And so really this boils down to the crystallographic symmetry. So for example, if you have the half-Heusler structure, which doesn't have inversion symmetry, then when you apply a force to the material in this direction, you would observe an accumulation of charges since it's not symmetric. There's no inversion symmetry, and so you might observe voltage across the material. However, if you have a material like diamond, which does have inversion symmetry, then if you were to apply that same force, you wouldn't observe a net voltage across the material. And so just by using symmetry alone, by one symmetry feature, whether or not it has inversion or not, you can easily screen whether or not a particular material would be good for a piezoelectric application. And so this is just one example where symmetry is important, but again, we'll kind of see more use cases where we can use symmetry to better understand the structure to basically guide materials discovery. And so another example that will actually kind of be, that we'll see a little bit more in more detail in the next session is this idea of prototype structures. So again, it has to do with this underlying structure or symmetry. And if you decorate these arbitrary atomic sites with different elements, you can get slightly different properties. So for example, here we have PT, SB, SE, and we're basically just changing this third element. And you can see, for example, the band structures, they're actually fairly similar, but we can see a slight tuning of the band gap just by changing that one element. So again, this idea of controlling the structure or better understanding it to kind of tune these properties is basically the goal for this session and then also the next session. Okay, so but to start, we are going to be discussing the AFLOW-SYM software. So AFLOW-SYM determines the invariance of a crystal under transformations. So basically what this means is we're transforming the atomic positions and trying to see if we can map them onto one another to identify some symmetry elements. So for example, we're trying to identify mirror planes, rotation axes, screw axes, glide planes, etc. And with this, we can identify certain descriptions for our crystal. So for example, the space group, the Bravais lattice, Pearson symbol, Wyckoff positions, if you're familiar, and then also different representations of the cell also depend on the symmetry. And so we'll see actually throughout the rest of the workshop that we're actually using symmetry in a lot of places. We already saw yesterday that we needed symmetry to determine the high symmetry K-paths. So for the band structure calculations, so we needed symmetry there. So that made our lives a lot easier when we were trying to create that K-point file. So we need it there. We'll see, I believe the last day of the workshop, we'll be discussing phonons. And again, you can use symmetry there. Again, you have these phonon dispersions. And so you would, again, plot those with respect to the high symmetry K-paths. And you can also use symmetry to reduce the cost of the simulation, which I'll show a little bit later. And I think also Dr. Esters and Dr. Smolyanyuk will discuss this as well. We can also use it to classify prototypes or classify structures, and we'll see that in the next session. And then at the end of today, we'll also see that when we're going to see the aflow.org repository. And basically, it's another way that we can categorize or find particular crystals in our repository based on these symmetry descriptors. And so since symmetry is used in all of these different places in AFLOW, it needs to be very robust. And so we've done many benchmarks, we've done lots of testing, and we've implemented a lot of routines to ensure that we get high consistency results. And I think we mentioned that we have over 3.5 million entries in the database, and AFLOW-SYM works for all of these without any human intervention. So it's a very robust code that we've been working on for a long time, even before I joined the group. And so I just wanted to highlight some of the ways that we're able to get high consistency symmetry results to kind of show you how we're able to do this at a high throughput level. So, but to better understand this, I first kind of want to take a step back and show you actually how we identify symmetry elements. So it may seem trivial because maybe you're thinking, oh, you can just look it up in a table, and then it's pretty straightforward. But actually doing this computationally, it can be very difficult. And so I'm going to try and highlight this idea in this slide. So the idea here is, given a particular geometry of elements, we want to determine what the symmetry relations might be between this configuration. So for example, let's say we have this diamond-shaped configuration, and we want to know whether or not it has a fourfold rotation that is basically a symmetry of this arrangement. And in order to do this computationally, essentially what we need to do is we need to take this original set of atoms, transform them by this rotation, and see if the original atom positions line up with the transformed atom positions. And so it turns out there's kind of three scenarios that you can have. So the first at the top is the ideal scenario. So if you apply the transformation, when you compare the transformed and original atom positions, they line up exactly. So you know, okay, this particular geometry has fourfold rotation. But on the worst case scenario, so at the bottom end, we see that, okay, maybe if we apply the atom or the transformation, maybe we had a 2-atom system. And if we apply the transformation, we actually don't map on to the same position. So this is not an isometry of the crystal or the symmetry of this arrangement. But really, the most realistic scenario we have is here, where when we transform the atom positions, we don't exactly line up onto the original positions again. And so the question is, should this be a mapping? And so basically what we need to do is we need to apply a tolerance cutoff or a tolerance threshold. And so a lot of times you have to do this for numerics or computation, and especially when you're working with real atomic positions, they're not going to be ideal. And so we need to have a threshold that says, okay, we're within this region, they're close enough, they match. And so the prescription here is basically you take all of the original atom positions, compare all of them to the transformed, and if all of them are less than this threshold, then that particular geometry exhibits that symmetry. So that's the general idea, but I kind of showed just almost like a molecule, but in essence, it's a little harder for crystals for 2 reasons. One, we have periodic boundary conditions, so we need to consider the method of images when we're doing these transformations. And the other difficulty is sometimes we're performing mappings in non-uniform metric spaces. So what do I mean by that? So we kind of saw this a little bit yesterday when we were talking about direct and Cartesian coordinates or fractional. So Cartesian or fractional, and fractional is sometimes referred to as direct. So what do I mean by this? So let's say that we have a particular cubic lattice and we have a tolerance sphere to represent, our tolerance threshold. And if we transform or basically represent our crystal in fractional coordinates, we notice that anything in fractional, if you remember from when we were generating those postcards, all of the positions were given with respect to the lattice. And so essentially we were representing the atom positions as if they were in a unit box. And so if you have a cubic lattice originally, when you represent it in fractional coordinates, you see just a uniform compression of the space. So we're kind of okay here. But if you consider an orthorhombic lattice, when you perform the transformation to fractional coordinates, you actually see that you're getting this compression of the space. And so you get this compressed sphere, so you get an ellipsoid. And so really this is what the distances or the epsilon looks like now if you represent it in fractional coordinates. And in the worst case scenario, in the triclinic lattice system, when you convert to fractional, again, you're forcing it to be into a unit box, you get the shearing of the space and you get the sheared ellipsoid. And so what this highlights is that if you're performing mappings or representing your crystal in fractional coordinates, which we were actually doing yesterday, then we need to be careful when we're performing mappings because the distance metric or the metric tensor is not uniform. So we need to be careful here when we're doing mappings. So how can this cause problems? So if we look on the right-hand side here we have a 2D crystal and we're trying to find a mapping. So we're trying to identify if this mirror plane represented by n hat m is an isometry of our crystal. So again, as I mentioned, we need to take the original atom positions and transform them. And then we need to do a minimum distance calculation between the original atom set and the transformed atom set to determine where the mappings are. And so in this case, the closest atom is given by this green arrow here if you do it in Cartesian. And so this method is very robust if you do it in Cartesian coordinates. It can be a little expensive because you need to consider the method of images and consider neighboring cells. If you do this in fractional coordinates, you'll notice again, this is the same system, but we've squished it into a unit box based on our definition of fractional coordinates. And if we do the same minimum distance calculation, basically we would minimize this vector, it actually turns out that you would find this is the minimum. Oh, sorry, I went back. This is the minimum distance here. And so you can see there's a mismatch. And so really what I wanted to highlight here is that minimum distance found in fractional coordinates and minimum distances found in Cartesian coordinates are not necessarily the same. And so we need to be careful about this. And this is something that the AFLOW symmetry software takes into account. So it takes into account the lattice skewness. So that's one way that we're able to get high consistency results. The other is we employ a self-consistent tolerance scan. So what I mean by this is, let's say that we had a particular crystal system and we want to determine its symmetry. We can choose different ranges of tolerances and we may get different symmetries as a result. And so this is actually a real system that we found in the ICSD database, where if you use lower symmetry or lower tolerance thresholds, you observe lower symmetry. And then if you employ a higher tolerance cutoff, you might observe higher symmetry. So for example, FCC at the top of the range and MCL at the bottom of the range. And so you can see we kind of have this spectrum. However, there is a hole here. And so this is what we call the confusion region in the tolerance spectrum. And what happened here is that we found incommensurate symmetry. So maybe you found, I don't know, 49 point groups, which is impossible based on crystallographic rules or crystallographic conventions. And so instead of throwing an error and saying we can't find the symmetry, we basically do a tolerance scan from this original epsilon value where maybe we found inconsistent symmetry, and we continue to scan the different, we change the tolerance, check the symmetry until we find consistent symmetry at a new tolerance threshold. And so with this tolerance scan, you're guaranteed to get self-consistent symmetry results via this tolerance scan routine. And the other thing that I want to mention is we use system-specific tolerance values. So if you're familiar with some of the other symmetry packages available to the community, they typically have default tolerance thresholds, and they're somewhat arbitrary, and they don't necessarily apply to all of your systems. Maybe this tolerance is good for one system, but not for another. And so what we try to employ is a system-specific tolerance where we consider the minimum interatomic distance as part of our tolerance threshold. And basically we scale the minimum interatomic distance by a factor. And so in this case, for tighter tolerance values, we use this default here. And for looser criteria, we divide it by 10 instead of 100. And also some of the other symmetry packages will use multiple tolerance values. So they might use an angle tolerance or a tolerance for even a specific symmetry operation. And so what's nice about AFLOW is there's kind of one symmetry tolerance to rule them all. So basically you input one value, or you don't even have to, and AFLOW will use that value consistently throughout the calculation. Okay, so now your question might be, okay, so now I've highlighted some of these, subroutines that help us to get high consistency results. How do we really compare to the community? So we did this benchmark. So for those who are familiar with some of the other symmetry packages in the community, we compared our results to FineSym, Platin, and SPGlib. And so here, for this particular test set, we took experimental structures from the inorganic crystal structure database, and we got the experimentally resolved symmetry. So the experiment reported a symmetry, we took that, and then we calculated the symmetries of these structures with the different packages. And here we're plotting the mismatch. So what we're plotting here is when experiment and the calculated symmetry did not agree. And so you can see that AFLOW is blue. And so we have the fewest number of mismatches overall, regardless of what lattice type you're looking at. And so you can see there's actually 2 bars for FineSym and the other packages. And basically, we use their default tolerance values for the solid bars, but then we're like, okay, what if we change the tolerances for their packages? What kind of results do we see? And that's given by these dashed bars. And so you can see the results change. Sometimes they get better. And so you can see that if you use these other symmetry packages, yes, you can get similar or better results, but the idea is that as a user, you would need to tune these by hand. And what I want to highlight here is that with AFLOW, you didn't have to put any external input. You didn't have to specify the tolerance. This is just the default tolerance that AFLOW gave you. And so this is, again, kind of a selling point for the AFLOW-SYM software, is that we get high consistency results with limited human intervention from the user. All right, so I guess, are there any questions so far up to this point? Again, feel free to post in the chat. So that first part, I just wanted to kind of highlight some of the new things that AFLOW-SYM does in comparison to the other softwares and how we actually calculate these things. But okay, so if not, I'll continue, but again, feel free to post in the chat. So now I'll kind of get it into a little more of the details about what we're actually calculating.
There's a question in the chat, sorry.
Oh, thank you. Can you elaborate the minimum in the Cartesian versus fractional space part? Sure. So yeah, let me go ahead and get back to that. So yeah, it's a great question. I know this is kind of getting into the details of how we actually calculate things. Okay, so just as a recap, so the idea here is that we're representing a crystal, which of course lives in the real world. So that's three-dimensional space, and typically we use Cartesian space. So this is a uniform metric space, right? So in Cartesian coordinates. But then, as we saw yesterday, when we actually represent things in fractional coordinates, we're scaling everything to the lattice vectors. And so what we're doing here is we're essentially converting any lattice, regardless of whether it's cubic, orthorhombic, triclinic, into a unit cube. And when we do this, you'll notice that the metric tensor is essentially no longer uniform. We're squishing the space. And so this means that actually, so for example, in this case here, the distance, since we compressed it, if we travel along in the fractional coordinates, we're actually traversing further along if we were in Cartesian coordinates. While here, we're kind of traversing in the same amount. But I would say if you're traversing here, you actually have a larger distance that you're actually traveling, even though you're not going very far in direct coordinates. And so because we had this squishing of space, it's essentially our metric tensor is non-uniform. And so we need to be careful when we're computing minimum distances here, because in Cartesian coordinates, we have a uniform metric. So there's no problem. We can calculate distances or minimum distances, no problem. But in fractional coordinates, again, it looks like this was the minimum distance that was found. But if we were actually to convert this back to Cartesian coordinates, which is what we want to do when we're actually determining, true distances between atoms in real space, we need to convert back to Cartesian coordinates, and we would see that actually this mapping we found here is not correct. So hopefully that helps a little bit. What happens to the epsilon in the fractional coordinates? So the epsilon, it's essentially getting smushed, or it's getting skewed. So epsilon, we're representing epsilon just as an example here. But in general, what we're trying to say is that the metric tensor is no longer uniform. And so again, maybe the orthorhombic is the best case, but essentially this tolerance sphere epsilon, in order to convert this lattice into fractional coordinates into the unit cube, we have to smush the space in order to get that unit cube. And so that's, so essentially that's what's happening to epsilon. Depending on what your original lattice is, it's basically going to transform your epsilon accordingly. But for cubic, as we saw, it didn't really make a difference because a cubic lattice looks the same as a fractional unit cube. So the last question is, so in actual testing, you consider the distance in Cartesian space? So that's a little more involved. So the answer is sometimes yes. We actually, I can kind of refer you to the AFLOW-SYM paper, but essentially we kind of determine when it's safe to use distances in fractional coordinates. Because in general, you can calculate things here, but the problem is if you transform it back and there's a mismatch, then you have a problem. And so we came up with a heuristic cutoff where if this distance is small enough, it's not really going to have a consequence in Cartesian coordinates. And so you can safely do mappings in fractional coordinates, because if your atoms are so close, let's say if the atoms were here, where my cursor is, then when you transform here, the mapping is going to be the same in Cartesian coordinates. So yes, I think Marco sent a link to the paper, I believe in the introduction somewhere. we talk about that tolerance threshold where basically we can safely calculate things in fractional coordinates, or we need to do it robustly in Cartesian coordinates because the distances or the tolerances are too large. So, but yeah, these are great questions. I know that this is kind of, a tricky part of the the slide. So I appreciate the questions. So yeah, I'm glad that that answered, I think, hopefully everyone's questions. And yeah, thanks again, Marco, for supplying the DOI to the paper. Okay. So yeah, again, the nice thing is that AFLOW is taking care of this under the hood. And so you don't need to worry about, whether or not you have the skewing in space. AFLOW is going to take care of that for you and make sure that it's doing it correctly. Okay, so now that we have some of the technical details out of the way, now I'll actually say, what are we actually calculating now? So we're calculating the symmetry operations. And so if you're familiar with crystallography and group theory, in this case, we're calculating, the rotations in our system. And so if you're familiar, there's the crystallographic restriction theorem. And so in crystals, you can only have a finite set of possible rotations. So you can either have twofold, threefold, fourfold, or sixfold. So we're going to be trying to find those in our system. We're going to determine if there's inversion points. So essentially, if we invert about a point, we see that we're actually flipping and also kind of reflecting along the other side. There's also rotoinversions. So these are basically rotations followed by an inversion. So for example, maybe let's see if I can use. Let's use the laser pointer so you can see a little bit. Okay. So in this case, so for rotoinversions, basically it's a rotation followed by an inversion. So for example, this guy here is going to rotate 120 degrees, and then he's going to flip here. So this is the second position. And then basically you would continue this process until you get the constellation of points. So these are rotoinversions. We also are determining glide planes. So basically this is a translation and a reflection. And then we also have screw operations. So basically this is a translation followed by or simultaneously with a rotation. So basically we're kind of rotating and translating at the same time. So we're finding these as well. And so collections of these form what are known as groups. So if you're familiar with group theory, a group is an algebraic set with certain axioms. I won't go into the details there, but essentially we can identify important groups for our crystals. So for example, you may be familiar with the point group. So the point group are the point group operations, so rotations, inversions, rotoinversions. Then if we add in translational invariants, since we're working with crystals, then we get what are known as the space group operations. So these are, again, the rotations, inversions, rotoinversions, plus screws, glides, and lattice translations. So this is essentially the full symmetry of our periodic system. And another type of group that I want to mention is what's known as the factor group. And so the factor group is essentially, I won't go into the details too much here, but it's a coset decomposition of the space group. So what we're doing is we're separating out the lattice translations with all of the other operations. So you can see we have the identity and the lattice translations here, and we're basically separating them out. And if we kind of isolate or kind of remove this right-hand side, this IT, what we're left with is this left coset, is what it's called here. And these form essentially the unit cell or the symmetry operations that are confined to the unit cell. And so this representation is really important because let's say we have a primitive cell and we want to know the symmetry operations that are in that primitive cell, we would use the factor group description. Similarly, if we had a conventional cell, which is a little larger, we would have a slightly different factor group because we essentially have a larger cell. And so we would have more factor group operations because we're representing the symmetry with respect to a particular unit cell. And so we'll see this a little bit more in the demos and exercises. And this particular description is used in other parts of the AFLOW code as well. Okay, so to summarize, there's different crystallographic groups we can calculate depending on what attributes of the crystal we're interested in. So for example, at the top, we have the lattice point group. So this is the point group of the lattice points. We have the reciprocal lattice. So this is the dual of this. So this would be the Brillouin zone symmetry. I mentioned the factor group. Then we have the crystallographic point group. So this is when we take into account the lattice plus the atoms. And then what is the symmetry of that? Then we have the dual of this, which is the irreducible Brillouin zone symmetry. There's also something known as the Pearson symmetry, which I won't really go into, but the space group, and then also the site point group, which is the atom point symmetry. So basically, if you center your origin on a particular atom, what are the rotational symmetries about that atom? And so this is important for phonon calculations as well. All right, so a few more slides and then we'll get into some demos, but the other type of description that I wanted to mention was we can analyze what we call the crystal spin symmetry. So for example, if you have a crystal system, it has space group 229. If you introduce the magnetic moment, let's say you have spin up on the origin and spin down in the center of these cells, then you can use the spin degree of freedom to break symmetry. And so you can see we get lower symmetry if we consider the magnetic moment. So again, this kind of goes back to some questions we got with can we model magnetic systems? And so this is one part of that where we can actually describe the symmetry of these magnetic configurations. And so in general, you'll observe this relationship where the crystal symmetry is a superset or it's equal to the crystal spin symmetry. And so just a disclaimer, this is not the same as the magnetic space groups. So that includes time reversal symmetry, which is kind of beyond the scope of this workshop. And as of now, we only focus on crystal spin symmetry, but future versions may incorporate these magnetic space groups. All right, so somebody asked, can we model magnetic ordering as a function of temperature? So that is a good question. I guess in general, we have the infrastructure, I think, to do so. At least we can generate these structures. And I guess we'll see a little bit more some of the thermodynamic properties and thermomechanical properties. As of now, we don't have a lot of magnetic support with as a function of temperature in AFLOW, but we do have some tools, I think, that can help model it. So yeah, I hope that kind of answers your questions. We do have some tools, but that's not something that we'll be showing in this workshop, really. But good question. Okay. All right, so some of the, so another thing that I want to mention is that AFLOW can give us a wide variety of different representations for our symmetry elements. Okay, so we know what they look like graphically, but we need to represent them mathematically and store them so we can use them in our computation. And so typically for translations, it's typically a 3x1 vector. For fixed points, so these are the rotations or inversions, rotoinversions, we typically represent them by a 3x3 matrix. And then for fixed point free is what they're called. So this is the screws and the glides. We basically combine the translations and the fixed point operations. But within this group, the fixed point group, this is a subgroup known as the pure rotations, or if you're familiar with some group theory and Lie group theory, these are the SO3. This is the SO3 group. And so you can represent this particular operation in many different forms. So you can do axis angle. There's something known as the matrix generator, which is the Lie algebra of this group. So it's a skew symmetric matrix. There's also quaternions. And so these are useful for computer graphics because you're essentially, instead of doing maybe a 3x3 matrix, you only have this 1x4 vector that you can use. So it can be a little cheaper. There's also the SU2 matrix and the SU2 Lie algebra. And again, these are kind of analogous to the SO3s. And so AFLOW will give you all of these representations when it calculates. So we'll do a calculation and you'll get all of these different representations so you can use them in whatever application you may want to use them. So you can actually extract out, okay, I want, the axis angle representation for this operation. So you'll have all of that information with AFLOW-SYM. So the other thing that you can get is the normal symmetry descriptions that you might be familiar with. So the space group number, the different space group labels. And then we also have consistency with the international tables for crystallography. So this is kind of the de facto standard for representing crystallographic symmetry. And so we're consistent with that. And so we can actually provide some of the descriptions that are consistent with this convention. So for example, we can determine the Wyckoff positions. So for something like this, the Wyckoff position, let's say, would be silver. It has a multiplicity of 4, meaning that there are 4 symmetry equivalent atoms for this set, an arbitrary letter designation, and then a single coordinate that if you apply the symmetry operations to this coordinate, you would expand out to the 4 equivalent, the 3 other equivalent positions here. And so what's nice with the AFLOW software is that we can give you this representation, and then it also understands that if I know the symmetry or the space group, I can expand out these positions for you, so you don't need to go look it up in a table and expand out the coordinates. The other thing I want to mention is that there are different settings or origin choices or cell choices in the ITC. And so you can kind of play with that with AFLOW. You can change the settings. So for example, for rhombohedral systems, you can represent it in a hexagonal representation. So which would be one of these, one of the 3 white boxes. And then, or if you want it in the rhombohedral setting, which is kind of this gray inset, you can represent it in there, in this representation as well. And so again, you can represent the Wyckoff positions in these different ways. Same with the monoclinic systems. There's 2 conventions known as the unique axis B and C. So basically how you label the axis or the axes. So again, we can toggle between that with AFLOW. And the other setting choice that you can play with is for centrosymmetric space groups. So there's essentially 2 origin choices. So you can center your origin on maybe a high symmetry site. So for example, for space group 227, you would center on this site in the crystal here, or you can center on the inversion site, which is located here. So you can see they have different site symmetries, and you can kind of toggle between where you want your origin to be. All right, so I think 1 or 2 more, and then we'll get to some of the demos. So the other thing that I wanted to mention is we can calculate things like the Pearson symbol. And so for those who aren't familiar with what the Pearson symbol actually tells you, here's just a quick kind of lookup table. So the first character is the crystal system. It's typically lowercase, so it could be, and it represents either triclinic, monoclinic, orthorhombic, tetragonal, hexagonal or trigonal, and cubic. So this is kind of the mapping here. And these, of course, have different lattice parameter constraints based on the symmetry. This second letter, typically capitalized, is the lattice centering. So it tells you how many lattice points are in your conventional cell. And so you kind of get this relationship between the number of lattice points between the conventional and primitive here. So for example, if you remember from maybe your material science classes, for a particular face-centered crystal, you have 4 lattice points in the conventional cell. And so there's a 4-to-1 ratio between the conventional and primitive cell. So anyway, so we have primitive, base-centered, face-centered, body-centered, and rhombohedral. And then this last number is the number of atoms in the conventional cell. And so one easy way to count this is you can just sum up the Wyckoff multiplicities. So if we get all the Wyckoff positions in our crystal, if we sum them up, so for example, in zinc blend, these are the 2 Wyckoff positions you have. And if you basically sum up the multiplicities, you would see that, okay, we have 8 atoms in our unit cell. And so this combined all together would give us a Pearson symbol of CF8, since we were kind of referring to this zinc blend structure. So again, this is something that's handled by AFLOW. It can give you this symmetry description. Okay, so I know I kind of went through kind of a brief overview of what we can calculate with AFLOW. Are there any questions up to this point? if there are, again, feel free to post in the chat. Otherwise, we'll start to get into some of the demos after this slide. But one thing that I wanted to mention is that a lot of the functionality that we're going to be discussing today, we've implemented online. So if you go to aflow.org/AFLOW-Online, then you can actually, load up a postcard, and then you can perform some of the symmetry operations that we're going to be doing today. So you can calculate the space group, Wyckoff positions, Pearson symbol. So probably as we're doing the demos, I'll try to refer back to this and kind of show you the analogous functionality online. So somebody asked, could I highlight the difference between the conventional and primitive unit cell? Sure, great question. All right, so yeah, let me go back. Oh, it's doing this video. Okay. All right, so the difference between the primitive and conventional cells. So in general, the primitive cell is the smallest representation for our crystal. So typically, there's only what we say one lattice point. So actually, if you see all of these gray boxes, all of these are a primitive representation of the particular lattice. So for example, in this case, you can see for this primitive centering, you can see that there's technically only one lattice point, because if you basically count, these are on the corners. And so you could say there's only one atom position or one lattice point, because if you count all of these, there's 8, and essentially there's only 1/8 of a lattice point in each cell. So there's only one lattice point. In this case here, we have a base-centered conventional cell. And so you can see that we have essentially 2 lattice points, because we again have the 8 on the corners, and then these 2 sharing a face. And so again, if you kind of consider the fractions, where the fraction of the lattice point that's in this box, if you count them all up, it's 2. And so the conventional cell is typically it can be a larger representation of the crystal that typically highlights the symmetry. And so, for example, if you have a cubic cell, for instance, the conventional cell, these lattice parameters or these lattice vectors will be parallel to an important symmetry direction. So for example, the cubic cell, these lattice vectors are parallel to the 4-fold axes. And similarly, maybe for the hexagonal system, the C-axis is parallel to maybe a 3-fold, or it could be also a 6-fold rotation. And so in general, I would say as a summary, the conventional cell typically is a representation of the crystal that exhibits or highlights the symmetry, while the primitive conventional cell is just the smallest representation. So it only has one lattice point in the crystal. So hopefully that helps a little bit. I tried to give a little different perspective on it.
David, can you also mention about how the AFLOW primitive is a little different than maybe some of the other ones, other primitive representations?
Sure, yeah. There's actually an exercise on that, or at least we'll show it. But the idea is, okay, so there's many different ways you can represent the primitive cell. So the primitive cell is not necessarily unique. You can form different ways where you can have, the smallest representation, the smallest volume of a crystal. There is a convention in AFLOW. So typically we use the AFLOW standard, again, kind of analogous to the AFLOW standard settings, but we also have the AFLOW standard symmetry representation. So we have the AFLOW standard conventional and the AFLOW standard primitive. And so in general, the AFLOW standard primitive, we chose it in such a way, again, actually we'll see it a little bit later, but I'll kind of highlight it. But basically it's a good representation for when we actually convert it to, again, as Dr. Osis mentioned, when we transform the crystal to the reciprocal lattice, we chose the real space representation such that when we convert it to the reciprocal lattice, it's the most orthogonal, which is good for plane waves because you don't really want to have a skewed cell in K space when you're working with plane waves. The more orthogonal it is, the better it is. So essentially we kind of work backwards from K space to describe what the AFLOW standard primitive cell is. So I'm actually going to highlight that a little bit more later on when we talk about the Brillouin zones. but yes, there, I guess the idea here is that the primitive cell is not necessarily unique. And I'll try to show some examples of that in the demo and in a later slide. But yeah, thanks for bringing that up. Okay. Oh yeah, no problem. All right, so the last thing that I'll show before we do some of the demos is we can also visualize the symmetry elements on the aflow.org webpage. So for example, again, we have over 3.5 million entries on the AFLOW database. And again, we've calculated the symmetry attributes of all these structures. And so we can actually visualize it. So maybe you're saying, I'm not sure where the fourfold rotation is in the system. So you can pull up the entry, and there's actually a symmetry interface where you can basically click on the symmetry element you're interested in, highlight the axis, and then apply. And basically you can see how the crystal maps back onto itself. So actually, let's maybe go ahead and navigate to just a particular entry page just to show you. So let me exit out of, oh. There we go, okay. So you can feel free to follow along if you want to open your web browser and type aflow.org. And we saw a little bit of this in the first session, but let's go to the Mendo Lib Search. So we're basically going to be searching for a particular structure of interest. So we're going to do, let's say, Na and Cl. So let's just do the example that we had. And we're going to restrict it to 2 species so we can hopefully find the same rock salt structure that we were looking at before. It should be one of the first ones that pops up. All right, so it looks like we have a lot of these. Again, the duplicates are because we have, there may be duplicates in the ICSD. And so let's just click on the first one. And so it's going to take you to a particular material entry page. And the JMO visualization is going to load up. And then if you see, there's a symmetry tab here. And so you can see these are, there's 48 point group operate, or 48 symmetry operations for this particular structure. And you can rotate the JMO viewer. And then I would recommend turning on this background supercell for better visualization. So basically you can see how the original atom positions will map back onto the other atom positions. So you can play with this. So for example, I'm going to do another 4-fold rotation. So you can see that this, let me zoom in a little bit. So you can see the rotation axis here. And then if we apply it, you can see that it rotates about this axis. And you can see it maps onto the other atom positions, maybe in a different unit cell, that's fine. And the idea is that if you apply it 4 times, since it's a 4-fold rotation, eventually you'll end up back in the same spot. So again, this is a nice tool if you wanted to, maybe if you wanted to teach crystallography in the future, or just better understand the symmetry operations in your system. This is kind of a nice tool that we've implemented. Okay, so I think the last thing I'll mention before the demos is I wanted to, again, just kind of bring it back home to an important application where symmetry is going to be important, not just for classifying crystal structures, but also in some of the calculations we'll be doing later on in the workshop. So again, symmetry can help you understand what crystal you have, but also it can help you reduce the cost of certain simulations. So for example, we'll be seeing phonons on the last day. And so again, if we're trying to model a certain phonon mode, we can use symmetry to essentially reduce the cost of the simulation. So for example, we can find what are the symmetries of the crystal. So we can find symmetry distinct distortions or symmetry equivalent distortions. And we also know that some of these atoms are symmetrically equivalent to other ones. So using these 2 facts, we can reduce what kind of distortions we need to model. And so you can see we can still recover the phonon dispersion. And here this is just an example where AAPL is the anharmonic automatic phonon library. And we compared it to some of the other off-the-shelf packages. And you can see that the number of static calculations that you need to perform to model these phonons is lower than some of the other packages. And this has to do in part to the symmetry that's being utilized here. And so again, we'll see this in phonons and also, I believe, in some of the thermomechanical modeling as well. Okay, so are there any questions about that introduction? So I know there was maybe a lot to take in, and we're going to see some of these examples. So maybe if you're not sure what the Pearson symbol is, or maybe further clarification on the conventional and primitive cell would be helpful. We're going to see some exercises on that. Okay, so let's go ahead and navigate to the VIDI portal. So let me go ahead and get it set up on mine. So, and at this point, I'm actually going to switch to the PDF version, so we can kind of have it side by side. Okay. All right, so for the exercises, as I mentioned, so let me just go ahead and get back to the desktop. So we're going to be doing exercises in day 2. So CD day 2. Then we're going to be going into the symmetry subdirectory. So O3 symmetry. And then let's go into the exercises. All right, so we have quite a few exercises. So what we're probably going to do is, so I think we have maybe about a half hour left. Yes, I believe so. So half hour left. We'll take a break and then we'll continue with the exercises or the demos, and then we'll do exercises as well. And we'll break off into groups. Okay. So what I want to highlight is that there's kind of 2 ways, or I guess there's 3 if you include the web. So there's 3 different ways that you can use the AFLOW-SYM functionality. So you can use the command line like we've been using in the past. We've also developed a Python module. So if you wanted to integrate this functionality into maybe your own workflow and use Python, then you can use this Python module, and I'll show both back to back. So I'll show you the command line version and the Python version. And then of course, there's also the web version. So maybe if you just wanted to quickly upload a structure and then just quickly get the symmetry, you can do that as well. All right, so let's go ahead and get started. So I'm just going to go through a few demos. So let's go ahead and go into the first directory, which is space group. And hopefully everyone can see. If you can't, I can increase the font size, just let me know. Okay, so let's go ahead and cap the README to see what we're going to be doing. Okay, so this first exercise, we're going to be determining the space group symmetry of the rock salt structure, so magnesium oxide rock salt structure, and I've given you the geometry.
There's a request to make the fonts a little bigger.
Sure, no problem. Thank you for bringing it up. It's kind of hard for me to tell if it's too small, too big. So let's go ahead and I think if people want to have this up as well, I'll keep it on the side. Perfect. All right, I'm glad. All right. There we go. Okay. All right, so let me just kind of clear the screen a little bit so we're back to. Oh. Sorry, I think my VIDI portal is still adjusting. There we go. All right, I caught up. Okay. All right, so let's go ahead and clear and then cap the README again. Okay, So what we're going to be doing here is we're going to determine the space group of the magnesium oxide rock salt structure. And we're going to first determine the space group number, then we'll do the Wyckoff positions, and then we'll do all of the space group related data. And so here I've given you some hints, which are essentially just the commands. And so let's go ahead and see what happens. And so on the left here, if you'd like, you can also see the commands here in a little bit more of a description. All right, so if we do, we can either cat the postcard, or we can do the redirect as it shows in the example here. So AFLOW minus AFLOW-SG, so this stands for AFLOW space group. And the first thing you should do, of course, is module load AFLOW. I forgot to do that. All right, so you should see that. And now if we run it again, you should see space group 225, and it looks like in the chat, yes, people got the same thing. So yes, you can see this is the label and then the space group number. So if you're familiar with rock salt, this is expected. For the Wyckoff positions, you can use this command here. So I'll do this variant next. I'll do AFLOW minus Wyckoff, sorry. And we'll pipe in the rock salt postcard. If we do this, then what we get here is, so we get the space group number, the setting, which I'll show you how you can toggle that a little bit later. What are the cell parameters? So this is A, B, C, alpha, beta, gamma. And then the Wyckoff positions for each site. So we have magnesium, and then we have 4A. So 4 is the multiplicity. A is an arbitrary letter designation that's given by the ITC. And then this is the site symmetry associated with that. And this position here, this is the representative Wyckoff coordinate. So if you expand it out, if you were to use the symmetry operations to expand out this coordinate, you would get 4 symmetry equivalent positions. And then also oxygen, same type of thing. All right, and it looks like in the chat, other people got the same result as well. And so next, let's say you wanted more than just, the space group number label and also the Wyckoff positions. So there's a command for that. So if you do AFLOW minus SG data, and then again, if you funnel in the postcard, you get SG data. And so there's actually quite a bit of output. So let me go ahead. Actually, I think it's probably better to show it on the left here. It might be too small, never mind. But basically, SG data stands for space group data. So it's giving you all of the space group related data that you might be interested in. So let's go to the top. So you can see, so you can see that we have the space group number, the different labels. So Hermann McGueen, Hall, Schoenflies, the Lau class, Crystal class, setting, origin. And then you also have the general Wyckoff position. So if you were to go to the international tables for crystallography, they basically have this table. But this is the general Wyckoff position. So for any arbitrary coordinate, this is basically what the coordinate would be given the symmetry operations of that space group. And then if we continue to go down, so you can see that there's quite a few those. And then the bottom here, we again have the representative Wyckoff position. So we have here, we have the positions. So again, the representative, and then again, that identifier information. So magnesium, site, multiplicity, letter, site, symmetry. And then at the bottom here, we have an expanded what we call Wycar. So essentially, like I said, AFLOW can expand out the Wyckoff positions based on the symmetry elements. And so you can see here, these are the corresponding 4 and 4 symmetry equivalent positions in the geometry file. And again, this is with respect to the conventional cell, which is essentially 4 times larger than the primitive cell would be. And we'll see that in later exercise. Okay, so it looks like somebody had a question. It seems we can't combine AFLOW-SG with Wyckoff together. Something like cat, MGO, rock salt, postcard. Okay. So yeah, in general, you can't, in general, you can't append, kind of separate commands together, because then the output might get a little muddled. And so that's why something like AFLOW-SG, if you wanted to get it all in one go, you would use something like SG data, for instance, or as I'll show in a second, the Python function. But in general, via the command line, typically the prescription is you have one command, maybe with some options, but typically you don't, tag on different commands in a single line. So I'd say for a majority of the AFLOW functions, you can't do something like minus AFLOW-SG, then minus Wyckoff in the same command, because essentially these both need to have the MGO rock salt postcar as an input, and it would get a little confusing for the commands if you run them like this. So somebody said there are 48 symmetry operations, but why it is showing 192? So you must be referring to the general Wyckoff coordinate here. Is that correct? Is that your question? If you can confirm. Okay, so this is the general Wyckoff position. And so in the international tables for crystallography, typically the Wyckoff positions are given with respect to the conventional cell. And so the conventional cell for face-centered cubic is 4 times as large. And so that's why we're seeing 192 and not 48. And so if you do 48 times 4, you get 192. So essentially it's giving you all of the positions as if it was in the conventional cell. So these are the general coordinates. Yep. Yeah, but great question. Again, that helps to highlight this distinction between the primitive and conventional cell. Because yes, you're right. In the primitive cell, if you were representing it in that representation, it would only be 48 within that cell. But in the conventional cell, it's 4 times as large, so 192. So yeah, great question. Okay. Excuse me, sorry. Okay, so are there any questions about the space group command line functions? Because if not, we'll go ahead and actually, so for those of you who like the Python interface, we can go ahead and try that. So let's go ahead and okay, so again, yeah, if you have questions, feel free to post in the chat while I'm navigating to this next one. Okay, so I showed you the command line, but now we also have a Python interface. So let's go ahead and view this Python file. So I'm going to do gedit, and let's see if it's a little easier to view here. Okay. So hopefully everyone can see. I'll zoom in just a little bit more. I have to go to preferences. Let's go to fonts and colors. And let's go to maybe 22. There we go. Hopefully that's a little easier to see. Okay, so for those of you who are familiar with Python, you can use the AFLOW Symmetry Python module. So for those who aren't familiar, I'll just give kind of a brief crash course. So, but basically at this top here, we're importing some libraries for Python. So particularly for this example, we're importing the AFLOW Symmetry module. So I'll show you in a little bit that we actually have a Python module in this subdirectory here that we're actually referencing. And then so we're importing some other libraries just to kind of print nicely. And so what you have to do is use the Python syntax to basically open a geometry file. So if you're familiar, this is the with open. We're opening this particular geometry file. We're going to read it in, and then we have some file handler for it, as we're calling it input file. We're instantiating the symmetry class. So the module wraps around AFLOW. So you need to have AFLOW installed on the particular machine. So, but basically you're specifying where the AFLOW binary is. And then to do, say, for instance, the space group data, you would do the sim.get SG data and use this input file handler. And then basically what it's going to do is AFLOW is going to calculate the result, and return a JSON object, or in this case, a Python dictionary. And so basically, we're going to have some key value pairs for those who are familiar with what the JSON structure looks like. So we'll have a keyword, let's say space group number. So that's the key. And then the value, it's going to basically return this value here. So basically, that's what we're doing here. We're going to print the results. So, okay, I'm going to go ahead and I guess I should close that. Did it close? Okay. So basically, I've already created the script for you, and it's already calling the correct postcard. So all we have to do is Python example. So basically, this is telling the command or the command line that I want to use Python to run this particular Python script. And if you do this, there's quite a lot of output, but at the bottom one I wanted to show you is, if you remember, the last two things I asked for were space group number, so it gave it to me. And then I also asked for the Wyckoff positions. And it's giving me the Wyckoff positions basically in this, this particular syntax, so it's a JSON object, or in this case, a Python dictionary. And so you can see that we have the same information that we saw via the command line. So we have the representative position, we have the species, so name, we have the multiplicity, the Wyckoff letter, the site symmetry. And so this is essentially enclosed in these brackets. This is the first position. And then since we have, or these curly brackets, and then we have another position here. So again, as expected, we have the two Wyckoff positions for the rock salt structure. And so what's nice about this particular form is, again, if you wanted particular attributes. So for example, one of the questions before was, maybe I want the space group and the Wyckoff positions. If you use the Python interface, then you can actually grab the particular keywords that you want. So in this exact example, you might want to use the Python interface to, okay, get the AFLOW-SG result, which is this, and then the Wyckoff positions here. And so above this, I printed the entire output, which again looks analogous to the SG data output, but it's formatted in such a way that it's in this kind of this JSON representation, so you can easily query it maybe in your own code. So yeah, there's quite a lot to scroll through, but so you can kind of see a similar syntax. So again, basically you have this key value. And so all of the SG data is just in this nice form that you can easily query. So I know it may be a lot for those who aren't familiar with Python, but hopefully that makes sense. If there are any questions, again, post in the chat. Okay. So it looks like, again, post in the chat if you have any questions, but if not, I think that'll be the end of this first demo. So this is basically how you can calculate some of the space group descriptions. So let's go ahead and navigate up one directory. The LS, let's go ahead and go into the 2SG settings. Right. And let's go ahead and cat the README to see what we're going to be doing here. Okay. So in this case, we're going to be changing the setting a little bit. So I mentioned in the introduction that we can change the cell representation that are consistent with the international tables for crystallography. So again, I mentioned this idea of for rhombohedral, you can do the rhombohedral cell or hexagonal cell, etc. And so what we're going to do is I'm going to actually show you some examples of how we can do that. So here I've again given you a refresher on what the different settings are. So again, you can have it for centrosymmetric space groups, rhombohedral, or monoclinic. And then what you would need to do here is you would need to append to the AFLOW command this option. So in this case, it's not a separate command like was referenced in the chat, but this is an actual option. So in this case, you would append it to a particular command. And so what we want to do is we're given a particular structure in each of these 3 subdirectories. And we want to play with this setting 1, which here's the map here. I also have it on the left here as well. And basically we want to play with setting 1 versus setting 2 and kind of compare the results. So let's go ahead and navigate into the first subdirectory. And so we have 2 structures. And so you could do the AFLOW command or the AFLOW-SG command, but that's not really going to tell you any setting information. You're going to see a difference in setting if you use the YCOF command. So what we'll do here is we'll do AFLOW ---- YCOF setting equals, let's do 1 for the first time, and then we're going to insert the beta Crystallographic postcard. All right, so AFLOW ---- YCOF, so we're going to be determining the YCOF positions, and we're going to use setting 1, and we're going to see what happens. Okay, so in this case, it was space group 227. So if you remember from this example here, this is space group 227. So this is the case of the centrosymmetric space group. You see here that we indeed are using setting 1. And what I want to highlight here is that if we use setting 1, the origin is on the high symmetry site. So in this case, the higher of the 2 symmetry sites is this -43M. And so you can see the origin is here. So we basically have our origin on this site. If you hit up on the command line, you'll get to the previous command again. That's going to be really useful when we kind of change these commands slightly. So let's go ahead and use the left arrow to get back. And now let's do the second setting. So we're going to put the origin on the inversion site. And let me just make this a little larger. And so let's change it to 2. Now in this case, you see, essentially we have the same symmetry, which is expected. You know, we didn't change this symmetry at all, but now we see we're using setting 2. And you can see now the origin is on this other site, which corresponds to the inversion site. And so essentially this is just an origin shift. But again, if you wanted to toggle between the 2, you can do that. And so we also have another example in here. So if you were to do the same for diamond, so again, if you hit up again, and then if you do it for diamond, and if you toggle between setting 1 and 2, again, there's only one atom or one YCOF position. And so in this case, setting 1, we're on the high symmetry site. And so you can see the origin. And if we do 2, you see that actually the origin is somewhere else and the atom is on this particular site. Great question. So in the chat, somebody said, is there an option to know how many settings are possible for a given structure or postcard? So in general, AFLOW offers 2, and actually there's a third option. But in general, the ITC typically reports 2 settings. Sometimes it reports more, but in AFLOW, we typically only have 1 or 2 settings. And so for a given structure or postcard, it's kind of hard to tell a priori because you need to know the symmetry first to know whether or not it actually has 2 settings. Because really, the 2 setting possibilities are only possible for rhombohedral, monoclinic, and centrosymmetric space groups. So you kind of need to know the symmetry beforehand in order to know if it has more than 1 setting. So yeah, it's kind of it's a little bit of a difficult question to answer because you really do need to know the symmetry beforehand to know. But in general, if there is an option, there's typically only the 2 settings that you can have, and these are kind of given here. So yeah, I'm glad that helps. Okay. But yeah, great question. So then let's just kind of see the other 2 quickly. So we saw the centrosymmetric. Now let's go into the rhombohedral. And we're going to do the same procedure. So we'll do, again, you can use the up arrows or you can type it again. So AFLOW minus Wyckoff minus setting equals 1. And let's go ahead and funnel in this Caswell-Silverite structure. And let's see what happens. So in this case, setting 1 for a rhombohedral system corresponds to the rhombohedral cell. And so what I want to highlight here is notice the Wyckoff multiplicity. So it's 1, 1, 2. And then also look at the lattice parameters. So it's about 7, 7, 7. They're all the same. And then also the angles are all the same. So they're all 30.4. So this corresponds to a rhombohedral cell, which is the smallest form, or it's one of the primitive representations. But if we change it to setting 2, we're going to represent this in the hexagonal representation, which we'll see is 3 times as large. So you'll see that the lattice parameters change. You know, we have 3, 3, and then 20. So the c-axis is very long. And then we have 90, 90, 120 for a alpha, beta, gamma. And then you'll notice that the Wyckoff multiplicity is different. And we have 3, 3, 6. So essentially, this is in line with the idea that the conventional hexagonal cell is 3 times as large as this primitive rhombohedral cell. And so this is a common setting in the ITC, so that's why we have both of these available. Okay, and then the last example we'll do for the settings is we'll go to the monoclinic system. So do cd .. /3 monoclinic. And then again, we're doing the same prescription. So AFLOW minus Wyckoff setting equals 1. And then we're going to do this Ascentiate structure. All right, so here, what I want to highlight, okay, so we have space group 15, which is a monoclinic system. And what I want to highlight here is notice the lattice parameters. So keep in mind that B is 9.2. So again, setting 1 says unique axis B. So in the B position, we have 9.23. And then notice that beta is the only one that's not 90. If we do setting 2, which is unique axis C, let's see how this changes. Again, you can see we have setting 2, but now notice that C is that 9.23 and gamma is 106. So again, this is just a different cell representation for the system. And you can see the Wyckoff positions themselves changed a little bit, but the actual multiplicities and the letter designations didn't change. Okay, so are there any questions about the space group settings? Okay, so maybe what we'll do is we have about 9 minutes until the break. So I think maybe what would be a good idea now is actually to show the corresponding web functionality for these two. And then for the next session, we'll go through some of the other demos, and then we will have some exercises. Okay, so somebody has a question. So we have the 2 different settings and they tell different possible arrangements of the basis atoms. If yes, can we directly generate 2 postcards for those settings? So it's not a silly question, it's a great question, and the answer is yes. So maybe I can show that. Let's go ahead and go back to, let's say, the rhombohedral, because I think that'll be a little more evident of how we do that. Okay, so if we do AFLOW, so we're going to do something a little different. Instead of Wyckoff, we're going to do Wycar. And then we'll do setting equals 1. And then we will do also right. So you'll notice the command is slightly different. Instead of ycof, we did ycar. And you'll notice that this looks just like a postcar that we've seen before. So that we have the title line, the scaling factor, and we have a little bit different of a representation of the lattice. Here we have the lattice parameters instead of the 3x3 lattice vectors. And then you'll notice that we have these direct coordinates, but it's just the representative ycof position, because technically these are, this is one position, and then two end positions. So what you can do is you can pipe it to another command, and you can do something like AFLOW --VASP. So this will create a geometry file for this guy. So you'll notice that now these positions have been expanded out. So we have CR, NA, and then 2S, which is consistent with the Wyckoff multiplicities. And we basically have the normal form that we would expect for a postcard. And so you can do the same for setting 2. And again, since the rhombohedral system, setting 2 does hexagonal. So we would expect it to be 3 times as large, which is indeed the case. So we see 3, 3, and 6. So yeah, that is a great question. And so yes, by using these two commands, I'm glad you find it cool, interesting. So yes, so that's the idea here, is that now we have a representation where we can analyze the symmetry, we have the Wyckoff positions, and then we can expand out the cell. And now we can, yes, you're right, we can compare these two representations. So yes, I'm glad you brought that up. And I just used AIMS to generate AIMS geometry file. So yes, so it seems like you're following along, and actually you're kind of alluding to something that we'll see a little bit later in the conversions. So I think today and tomorrow we'll show you how you can change the representation, but also change the format. So you can change it to something like AIMS. So you can generate a geometry file for AIMS or for Abinit, Quantum Espresso. And oh yes, thank you, Andre. So Andre gave the commands in the chat. So in case you missed it, this is basically how you can analyze the Wyckoff positions, change the setting, and then convert it to a postcard that VASP can then understand. So yeah, excellent, great question. So with that, we've got about 5 minutes. If there's any other questions, again, post them in the chat. I'm happy to answer. And while we're waiting, I'm going to go ahead and pull up the web, and we're just going to show these features on the web as well. So let me go ahead and go to this guy. And again, I encourage you to follow along. And yes, good point, Corey. So, or you can do VASP 5. So you'll note it. So sometimes there's different versions of VASP. If you're familiar with the difference, the generic VASP uses VASP 4. So you'll notice that there's no species indicated, in any of these lines. But with VASP 5, one of the things that they want now is they want to have the species just above the number of types. And so you can do that as well. So yeah, we'll see actually in the next session, session 4, when we're actually creating new geometry files, we'll see how we can convert to all of the different geometry file formats that AFLOW supports. So. Okay, so let's go ahead and open the web browser. So again, if you go to aflow.org, and I want you to click on AFLOW-Online. So this is a place where we have a lot of the AFLOW-Online tools. So let me just zoom in a bit. Okay, so I think we'll be referring to this a couple of times throughout the workshop. So if you go to aflow.org/aflow-online, that'll take you right there. And you can basically upload a particular structure. We support, again, the different file formats that we'll actually see a little bit later, but Postcar is definitely one of them, AIMS, SIF, many others. I'll go through a comprehensive list in session 4. So, but we have a geometry file, and then you can control the output type. So again, I mentioned you can have the plain text or the JSON, and then you can change, for example, the symmetry tolerance. So if you remember, we'll see a little bit later, we'll actually see in another exercise this type loose. But what I really want to highlight, since we just did the exercises for it, are the space group and the setting. So you can do space group, setting 1 and setting 2. One thing I didn't really mention, because I was going to mention a little bit later, is there's a third setting. It isn't actually a third setting, but it's what we call the AFLOW standard. So in general, we typically use a default, whether it's 1 or 2, so whether or not we use the rhombohedral or hexagonal cell. And so the AFLOW standard is basically the one that we prefer to use. So typically it's, B unique axis, or the rhombohedral setting or hexagonal setting. And so this is just the choice. We're going to see this in session 4 a little bit later. But so let's just go ahead and do setting 1, and then we hit submit. And you can see that we get some of the space group information here. And then you can see that we did setting 1. And then of course you could change it. You could try to change it to setting 2. In this case, I didn't see what the symmetry was. I don't think it was it was 225. So you'll notice, even though I said try setting 2, there's only one setting, so it's not going to change it. And so this command looks, or this output looks slightly different. That's because it's using a slightly different command under the hood. I'm going to show you at the very end the AFLOW README, so you can see all of the commands, because obviously we don't have enough time to go through all of them today. But I'm only going to be showing a subset of the command line functionality. And so I would encourage you, if you're interested in this functionality, to look at the README to see what other things you can kind of calculate in different forms, formats, and things like that. So I think we're, okay, great question. So how do we go to this page? So if you go to your browser, and if you just type aflow.org/ okay, yep, Marco beat me to it. So yeah, that's the URL. So if you just type that in your web browser, it'll take you to this page. The other option is you can navigate there from our home page. So if you're on aflow.org, and if you scroll down, we have some apps. And this is in particular the AFLOW-Online app. So if you click there, you'd also get here. And then just as a reminder, so you can upload your own postcard. So we just have an example one here, but you can upload your own. And then what you need to do is whatever analysis you want to perform, you would click on it. So you can see that it's purple now. And then you just hit submit, and then it'll calculate it for you. And so I'll be referring back to this. I guess the other one we can do is the Wyckoff positions while we're here. Let's go ahead and do setting 1. Again, since it's space group 225, we're not really going to see a difference. But you can see here's the expected output. Okay, and so yeah, I'll refer to this again in the next part, and we'll be calculating some of these other things as well. So this is, I've only really covered the symmetry descriptors, then I'll actually go through a couple more, such as the Pearson symbol, the different lattice types. And then at the very end, I'll also show you how you can calculate the explicit symmetry group. So you can find, okay, the rotation axes, get the 3x3 matrices, and things like that. Is 225 default? No, it's not the default. It's actually being calculated on the fly. So actually, if you're asking if the space group of this structure is 225, of the default structure, yes, it is 225. But it's actually calculating under the hood what the symmetry is. So it's not a default value, it's actually what's being calculated. So it's being calculated as space group 225, consistent with the international tables for crystallography. So for space groups, you can have between space group 1 and 230. And so based on the atomic arrangement and the symmetry, it found space group 225. So hopefully that answers your question. Any other questions before we take a quick break? Okay, so if not, yes. So Marco's right. Yeah, we'll probably actually see 225 a lot in the exercises, just because I guess my favorite structure is the rock salt structure. So space group 225. We will see other ones, but yes, space group 225 is kind of one of the common ones, and it's there isn't a lot of Wyckoff positions, so it's easily to check. How do I check for other space groups? I guess I'm not exactly sure what you mean by your question. AFLOW is calculating the space group based on your input structure. So it's going to calculate whatever the symmetry is of your structure. So it'll, if it finds a particular symmetry and that corresponds to a particular space group, that's what it's going to find. If you're looking for like a reference on the different space groups, I would recommend if you look at the international tables for crystallography. I think there's some things online, and that basically they have tabulations of all the possible space groups and all the Wyckoff positions. But again, that doesn't tell you what it is for your particular crystal. It's just saying, given this space group, this is what the possible Wyckoff positions could be, but you would actually need to feed in a structure to say, okay, these are the populated Wyckoff positions for my structure. And again, yes, we will see other space groups. Again, I only was able to show the 2 examples as of now, which were I actually did show some of the monoclinic space groups and rhombohedral. So for the rhombohedral space groups, those I think were 166. Yeah, 166. So we are getting different space groups in these different exercises. And for monoclinic, that was space group 15, I think. So yeah, and I didn't actually cap the output, but this is essentially the output or in this case, this is the input we're getting. So you can see it's a little different than, it's 3 times as large, or 3 times as small compared to the conventional cell. So this, basically, we are calculating things based on real structures. Yes, that is correct. Good point, Marco. So we're going to be talking about crystal prototypes in session 4, and we're going to be talking about how you can, one, create different structures, but also create structures in particular space group characterizations and have different Wyckoff populations. And so we're going to see essentially a range of different structures with different space groups. So yes, that's a good point. So welcome back, everyone, to Symmetry Part 2. So we're going to be continuing with the demos, and then we'll have some time for exercises. I guess one thing that I wanted to mention before we get started was somebody brought up a good question during the break, and so I'm actually going to share my screen one more time for the AFLOW-Online. So I think maybe it wasn't clear, but on the AFLOW-Online, we have an example postcard structure, but, and it happens to be space group 225. But if you want, you can upload your own geometry file. So all you need to do, I already have one in my clipboard, so I'm just gonna paste it. So this is actually one of the rhombohedral examples that I had. And so you can actually upload any structure in many different formats. We'll see in the next session all the different formats you can do: ab init, SIF, the YCAR, but you can upload your structure, change your setting, and submit. And so you can see now it's not space group 225 anymore because it's analyzing the symmetry of the example or the structure that's in the input, which is space group 166. So you can feel free to upload whatever structure you want. And so again, if you wanted to do it from the portal, again, you just need to use the clipboard feature that Professor Toher mentioned. So, okay, so with that, are there any other questions maybe from the last part that people had while we're getting set up? maybe while you're grabbing coffee or something, you thought of something. If you did, feel free to post in the chat. Otherwise, I'm going to go ahead and if you go back to the video portal and to the exercise folder. So again, if you're not sure where you are, you can just kind of type tilde desktop day 203 exercises. That'll take you wherever you are to this directory. So now hopefully we're all back to the exercise directory. Okay, so first we calculated the space group and Wyckoff positions, we changed the settings, and now we're going to do what's called the extended crystal data. So basically this is everything under the sun, I guess, for symmetry with respect to crystallographic description. So again, we're working with crystals, and whatever description we can think of, basically, hopefully it should be in this one kind of command to rule them all. So let's go ahead and go into this directory. So 3 extended crystal data. We do ls. We see we've got a few files in here, so let's cat the readme to see what we're going to be doing. Okay, so we have this particular structure. So we're going to determine the following symmetry descriptions for the Weberite or Weberite, not 100% sure on the pronunciation. But of this particular structure, which I've given you, and we're going to determine the Pearson symbol. So I discussed that a little bit in the introduction. So we're going to determine the lattice centering, the lattice type, and then the number of atoms in the conventional cell. So that's the Pearson symbol. Then the Bravais lattice type and variation of the crystal, the Bravais lattice type of the lattice, so ignoring the atom positions and just considering the lattice points, and then what's called the extended crystallographic data. So these are the corresponding commands that we're going to be running. So let's go ahead and just cycle through them and see what we get. Okay, so what we can do is we can either cat or use the funnel. I'm going to use the cat this time. So cat, and then we're going to use the Weberite, and then pipe to the AFLOW command, which will be AFLOW --. In this case, the first one we're doing is Pearson. And again, just in case you closed out of the video portal, make sure that you load the AFLOW module. So module load AFLOW. And so in this case, the Pearson symbol is OI44. So just to kind of go back to what that actually means, in case you need a quick refresher, it's on slide 16. And so again, the first letter tells you the crystal system. So O is orthorhombic. The second capital letter is the lattice centering. So I, so this is a body-centered system. And there are 44 atoms in the conventional cell. So that's the Pearson symbol. And typically you'll see this a lot when crystallographers are referring to a particular crystal structure. And so this is a good descriptor to know or be able to calculate. So if we hit up on the arrows, we can do the next command, which is lattice type. So this is similar to the Pearson symbol, but instead of the number of atoms, basically we're saying this is ORCI. So there's kind of some shorthands in the community for the different crystal systems. So ORC typically refers to orthorhombic, and then the I stands for body-centered orthorhombic. And so in this case, there's 2 values that are here. One is what is the lattice type, and the other is the variation. The variation is going to be important for the band structure calculations that we'll see. So we were kind of doing this under the hood when we did the kpath command, and I'm going to be discussing that in a little more detail. But I guess just for now, know that AFLOW -- lattice type gives you the lattice type and variation, and it just so happens that in this case, they're the same string, but they won't always be that. And so I'm going to show another example in a little bit. So that's the lattice type. The other thing is, so the lattice type considers the lattice positions or the lattice and the atoms. But maybe we just want to know the Bravais lattice of the lattice itself. So ignoring the atomic positions or ignoring the atom basis, what is the symmetry of the lattice? So you can do the same thing. So if you hit the up arrow to get to the previous command, you can do lattice, lattice type. Unfortunately, it isn't really too interesting for this example. I believe they're the same. But in some cases, you'll actually see that this value will change depending on what the decoration of the lattice is. And so the other command that I wanted to mention, I guess let me go ahead and go back to the corresponding slide, is edata. So edata, let's remove all of this and then type edata. And this stands for extended crystallographic data. And if we hit this, then it'll take a little bit, might take a few seconds because we're actually calculating a lot of things under the hood. So it seems like it's a little difficult for me to scroll in the Vidi portal. So I'm actually going to go to the slides here. I actually put the output in the slides. So, and you can feel free to look at the slides or the terminal, whichever you would like. But so this is the data output. So you're getting information about the real lattice. So this is the 3x3 lattice. Then you're also getting information about the lattice parameters. The lattice parameters in a different format or different notation. So typically we give them in angstroms and degrees. In this one, another convention is bores and degrees. The real space volume of the unit cell. The real space C/A ratio. And again, I don't think that these numbers may not line up with the example I have here. This is just for an FCC system, and I think this one was ORCI. So the results may not be one-to-one here because it's a different calculation, but the type of results are the same. Then we have the Bravais lattice of the crystal. So this is taking into account the symmetry of the lattice and the atom positions. So this is the Bravais lattice type variation. It's the cubic lattice system. Here's the Pearson symbol. Then some point group information. So the crystal family, crystal class, the different point group symbols. Yes, OI in the chat, OI44, yes, that's the Pearson symbol for this first, this example here. Then you'll notice that I have this SG data info and star. So actually, right after this, you should see the space group information. So you, just like the SG data command, you're going to see that's also in here. Then after that, you'll see the Bravais lattice of the lattice. So this is ignoring the atom basis and what is the symmetry of the lattice itself. Here, we determine what's known as the superlattice symmetry. So this is the symmetry if we took all of the atoms in our crystal and decorated them with one type, a single type. So for example, if you had rock salt, for instance, so sodium and chlorine, if you were to decorate them both with, let's say, sodium, then that would, you basically recover more symmetry, or you could recover more symmetry because basically those atom positions are now of the same type, so they might map to one another. So that's what the superlattice is. Basically, it's the symmetry of the atom positions, ignoring type, if you will, ignoring atom type. So in this case, this is the superlattice lattice. Then again, similar descriptions on the lattice parameters. And you'll notice that in this case, originally we had FCC symmetry, but then if we decorate the sites equally, we get cubic now. So again, we kind of got higher symmetry, and the Pearson symbol for this description is CP1. Then there's reciprocal lattice information. So again, the reciprocal lattice, the variation, etc. And again, if you're familiar with crystallography, and when you convert an FCC lattice, a real space lattice, into reciprocal space, its dual is the BCC lattice. So you can see that we are recovering the expected result. And then at the very end, we give two different representations of the crystal. So essentially two postcards. So this first one is what we call S-prim, which stands for standard primitive. So as Dr. Osis mentioned or referred to when we were discussing the different conventional versus primitive, this is the representation for the primitive cell that AFLOW prefers to convert to. And so you can see this is the particular representation. It's the smallest possible representation, and it has this definition of lattice vector. So basically zeros along the diagonal, and then essentially that A/2 that we saw before in the DFT lectures. The conventional cell is here, and you'll notice since it's an FCC lattice, it's 4 times as large. And here is the corresponding postcard. And you'll see now that the lattice is a cubic lattice because it's the conventional cell. And then here are the total of 8 atoms. So that's the extended crystallographic data. Are there any questions about this representation or this particular command? So the other thing that I wanted to mention, so that was the command line, but again, we also have some Python functionality. So if you look at the example.py, again, actually, let's use gedit. So gedit example.py, you can see this is the Python script. So it's going to look very similar to the one that I showed you before. You do the normal loading of the Python module. You need to input whatever structure you want to analyze. Instantiate the symmetry class, specify the path to the AFLOW binary. And the only thing that's going to be different is you're going to use this, this get edata method for calling it. And we're going to print the entire output, and then we're going to target particular keywords. Oh, thank you for mentioning that. I don't know if we're recording. I may have forgot to record. No, I think
started it.
Thank you,
Yeah,
Lisa.
I
Sorry.
started it.
Thank you, Lisa. I forgot. But yes, and thank you for at least double checking. All right, I'm glad it's still recording. Okay, so the Pearson symbol. So for example, if you wanted to query the Pearson symbol, you can grab that particular keyword and then it'll output the result. Same for the Bravais lattice type and Bravais lattice type. And so let's go ahead and close this. And let's actually run the script. So Python example. Again, there's going to be a lot of output to the screen. And all right. And so at the bottom, the very end of the script, I asked to print the Pearson symbol. So we see that's the result. And then the Bravais lattice of the crystal and the lattice. And then if we were to scroll up, you would see essentially the same edata information, but it's in a JSON form. So again, you can easily integrate this into your workflow and you can grab whatever symmetry attributes you need. And that includes a representation of the crystal. So you'll see all this name, occupancy, position. So this is actually the structure file essentially in a JSON form. So it's kind of like the postcard, but in a nice way that you can easily grab this information. So again, it might be useful for integrating into a Python workflow. So one thing that I want to mention is this edata output. You'll notice that we're actually calculating many different things for a single structure. And so we're calculating attributes of the lattice, the crystal, space group. And I want to mention that all of these descriptions are going to be self-consistent. And so if you remember back to that tolerance spectrum, basically we have an adaptive tolerance scheme. So let's say we're doing this analysis and we notice that, remember I said that the reciprocal lattice should be BCC, right? Because we know that the FCC real space, or we know in real space it's FCC. And so we have some consistency checks where if things don't make sense based on crystallographic conventions, there's probably a tolerance issue. And so basically we'll go back and change the tolerance, and then we'll recalculate everything to make sure that the superlattice is consistent, the space group is consistent. And so again, other codes won't necessarily do this because they don't have this tolerance scan functionality, and they don't necessarily calculate everything in one go. And so again, this is kind of an advantage of AFLOW-SYM, is you'll calculate everything self-consistently, so you shouldn't see discrepancies between the space group and the lattice symmetries. They should be consistent with crystallographic conventions. Okay, so are there any questions about the extended crystallographic data? I know there's a lot of information in there. Again, a lot of this will be in the AFLOW-SYM paper that Dr. Esther's provided in the chat, so you can feel free to look at that. At the end, I'll show you the different AFLOW symmetry README, and you can see the different commands and the output as well. Okay, maybe one more thing that I'll mention while we're here is, so I showed you the command line version and the command line output, and then I showed you the Python, but maybe you're wondering if from the command line you can change the format. And that is indeed the case. So if we do AFLOW, so again, let's cat the structure. We're going to pipe it to the AFLOW command edata. And then you can add this option print equals, and let's say you want to do a JSON. If you do this, it's going to do the edata analysis, and then it's going to format it in a JSON form. So there's no spaces, because basically we want to save space, especially if we're saving this into a file. And so all of the information there, it's not very pretty to see, but if you were to pass this to a nice function to render it properly, you would see that you have a nicely formatted JSON. So again, you can use the command line and then use this print option to control how you want to print. And currently we support the text format and the JSON format. All right, and then I guess while we still have the web open, you can do the same thing. This analysis on the web. So again, if you have a structure up here, and then if you scroll down and you go to crystallographic data here, there's a few different things. You can do data, which is just basically lattice data, not really a symmetry analysis in it, but you can do extended data. You can submit it. And you'll see we get the same result that we expected. And online, you can also control the formatting. So if you scroll back up to the symmetry tolerance, or sorry, right here, plain, the output type, you can do plain text or JSON. And if you submit, now it's in a JSON, and here on the web, we format it in a nice, pretty way. And so you can see all of the attributes, again, key value pair. So you can easily query this and use it for your own workflow. Okay. Any questions so far? Does that make sense? Okay. So I think now we can go back to the exercises. So if you go up one directory, cd .. ls. So we've done space group settings, extended crystal data. Now let's do conversions. So cd for conversions and ls. And let's cat the README to see what we're going to be doing. All right, so there's a little bit at the top here. Okay. So again, my favorite structure, rock salt. So MgO rock salt, I've given you the postcard, and we're going to convert it using the following, or into the following forms. So we have the ABC car, Y car primitive, AFLOW standard primitive, AFLOW standard conventional, Niggli and Minkowski, if you're familiar with those representations, so typically the most orthogonal and the shortest lattice vectors, and then a supercell, so you can create a larger cell. And so you can do that via the command line, via these options here, or these commands here. So these hints are essentially the commands. So let's go ahead and ls, and let's just go through the first one. So we're going to do ABC car first. So we can cat the postcard and do AFLOW -- ABC car. Okay, And you'll notice that it has car at the end. So that's kind of indicative that it's going to be something related to VASP, because we have POS car, cont car, in car, etc. So ABC car looks just like the normal post car, but you'll notice that instead of the 3x3 lattice, we have the lattice parameters. So again, on the left here, this is an example. Essentially, it converts the post car or any geometry file, as we'll see in the next session, to the ABC car. So again, this isn't too different from the post car, just it gives you the lattice parameters fairly quickly. Okay, so the next one was, let's do the Y car. So actually, we already saw this before, but let's do it again. So instead of the ABC car, we'll do Y car. So this is essentially the Wyckoff version of the post car. Again, it ends in car. So you can see here, the Y car, it again looks very similar to the ABC car, but we've done a symmetry analysis under the hood. So we have the lattice parameters for the conventional cell. Again, remember when we're referring to the ITC, typically the cell is given with respect to the conventional cell. So basically we have a 3, 3, 3, and then 90, 90, 90. So it's a cubic conventional cell. And the second number is the space group number, so 225. And then this next number is the setting. And we've already discussed the settings before. And then I think we already discussed that these are the representative Wyckoff coordinates. And then you also have the Wyckoff information to the right here. And again, with this command, I think we already saw you can change the setting. But in this case, since it's rock salt, setting 2 doesn't do anything because there's only one setting for space group 225. And then as one of the questions kind of prompted, can you create a geometry file from this? Again, you can kind of chain the commands via pipes. You can do VASP and VASP5, for instance. So again, you can kind of see the different ways that you can convert back and forth. All right, so let's cat the readme again just to see what the next one is. Okay, so next is the AFLOW prim. So what we're going to do here is we're going to do something a little different. Let's actually do the SCON first. So, okay, if we cat just the postcard itself to screen, we see that it's already kind of in the primitive representation. It's a small representation. But we can do the standard conventional. So this is the AFLOW's definition of the standard conventional. There are a couple of other definitions, and we'll kind of see another one a little bit later on. But we can do AFLOW minus SCON, and this is telling AFLOW that we want to convert the structure into the standard conventional form. And so if we do this, you can see we have a larger cell. And again, it's the conventional cell as expected. But then you can also do the standard primitive. So we're actually going to take the output from this sequence of commands, and we're going to do the primitive. So AFLOW S prim. And you'll see that, okay, so first, if you look at the command, we use this as the input to this command. We determine the conventional cell, and the conventional cell is the input to this next command. So you can see that basically we took it, made it larger, and then converted it to S prim. We can do the same. So that's S prim's, if it has an S before it, it means standard. So it basically we're referring to the AFLOW standard. And then if it just has prim, so no S, then it's just a random primitive representation. In this case, you'll notice that it's not necessarily the same. So look at the lattice vectors. So we have zeros along the diagonal, but in this case, we don't have zeros along the diagonal. You can see we have 0 here, 0 here, and 0 here. So these are both a primitive representation, but they are in slightly different representations. So most likely they're either rotated or they could be skewed in a different way, or maybe longer in one direction, shorter in another. But they are both valid primitive representations. And so that's why in AFLOW we have a standard. So that way, again, we're trying to make things standardized. and basically have it as homogeneous as possible in our database. And so that's one of the reasons why we have these standard conventions. And so here's the slide. So again, if you wanted to refer back later, this is essentially what we have here. All right, so cat the README. So we did the prims, the scond, and you can also do Niggli and Minkowski. So again, let's just kind of add it to this last command. So we can do Niggli. In this case, I should say that Niggli doesn't do a primitivization. Niggli will just try to take, I believe it's the most orthogonal structure. And so you get this, and you'll notice that you have some negatives here. So it's, again, not necessarily the same as the standard conventional representation that AFLOW has. And you can do the same for Minkowski. And again, you can see it's a little different than what Niggli would give, but you can see that, again, it transformed it, and it actually didn't transform it from the standard conventional cell. And then, yes, in the chat, you can see, yes, just for fun. So yeah, we can do that example here. So again, if you do scond and then sprim, or sorry, prim, you can see that, I think in this case, let's see what the original postcard was. Is it the same? Okay, so it's in a slightly different form. It is rotated. But if you instead did sprim, I think you would get the same form. Yeah, so in this case, the original postcard, if you do scond then sprim, you get the same result here. So yep, which is good because we would hope that it's consistent. And indeed, I think when we generated the structure, we were giving it in the sprim form. Okay, so then the last exercise was maybe you want to make a larger cell. And this particular functionality is important if you're trying to model phonon calculations. So a lot of times you may need to create supercells. And so this functionality is done under the hood in a lot of the phonon calculations that we'll see. But you can also do it via the command line by just doing cat MGO and then AFLOW supercell. And you can do, there's a few different input types. I'm just going to show one of the simpler ones. So 3 by 3 by 3. So this is uniform expansion in all three directions. You can see there's a lot. But there you go. You can see now there's 54 atoms. And so there's, at the very end, I'm going to show you some of the AFLOW READMEs. And so you can kind of see some of the different options for some of these. And there's different ways that you can use the supercell command as well. Okay, and then for the Python, we've implemented some of the conversion functionality, but really, if you go to the example, I'll go to gedit. Again, we're using this get edata data, but we can call the AFLOW standard primitive structure and the standard conventional structure. And so if we do this, we run the script. What I've asked the script to give us is the primitive is above here, and then the conventional is here. So basically, you can see this is a JSON version of the conventional cell. So again, hopefully it's useful if you want to use it in your own workflow. All right, are there any questions about conversions? So for conversions, I only really talked about converting the cell shape or the geometry itself. I didn't talk about file formats yet. That'll be in the next session. So there are, again, more commands that we can play with that'll convert the file format away from postcard into some other ones that are used in the community. Okay, So let's go ahead and go to the next one. Again, feel free to post in the chat as you get questions. All right, so let's go ahead and go up one directory. And now let's go into directory 5, which is the symmetry operations. All right, so up to this point, we've been using AFLOW-SYM to calculate common symmetry descriptions. So the space group, the lattice type, variation, Pearson symbol. But now, let's say you actually wanted to get the explicit symmetry operation. Yes, idempotence is fun. And so let's say that you want to extract maybe a particular rotation out, because maybe if you wanted to rotate the structure on your own, or maybe there are certain symmetry properties that if you transform them via the symmetry operations, then you get certain properties back out, or you can reduce the cost of your simulation. And so we actually explicitly give you these symmetry operations so you can use them if you'd like. All right, so let's go ahead and first let's cat the structure just to see what we're looking at. So by the name, you can guess that it's magnesium oxide rock salt favored structure in the standard conventional form. So just as a sanity check, you can see, okay, we have magnesium oxide rock salt structure in the conventional form. So let's cat the readme. Okay, so what we're going to be doing here is we're going to calculate the explicit symmetry operations for the point group. Oh, sorry about that. There we go. We're going to calculate the explicit symmetry operations for the point group of the lattice. Sorry, this is a typo, crystal, the factor group, and the space group. And so I mentioned before that there are different groups that we can calculate. So again, the lattice point group, the factor group, Patterson symmetry, space group operations. And so we calculate all of these, and since there's a lot of output, we typically save it to a file. So we typically do AFLOW dot and then whatever group alias we've given it. So again, P group would be the lattice point group, P group xtol would be crystallographic point group, F group, etc. And if you remember, and again, this should be a dot. And if you remember, when we did the AFLOW runs, I mentioned that there were some symmetry files that were printed out. So when we do AFLOW -- run, it's doing this symmetry analysis and it's giving us these symmetry operations. And so today we're actually going to see what are in these files. And so the other thing that I want to mention is, again, we support the 2 file formats. So there's the text and the JSON. And what we're going to be doing here is we're going to calculate all of the symmetry operations in one go. So all of these descriptions we're going to do in one command. And that is what we just refer to as the AFLOW-SYM command, because it's kind of the canonical command. So let's go ahead and do this. And we do cat mgo rocksalt scon.postcar. And we're going to do AFLOW -- AFLOW-SYM. And I believe I added some overloads, but I would just say be sure to keep in mind case sensitivity, just in case. All right, so actually allow was output to the screen and it was kind of difficult to see. So I'm going to go ahead and run the command again, but I'm going to, again, kind of like we did when we did the AFLOW runs. I'm going to put all of the output to, all right, there we go, symmetry.log. All right, and then let's go ahead and do gedit, symmetry log. So this is what was being printed to the screen. And so basically it's symmetry messages. So it says we're starting with this tolerance. Again, it was automatically determined by AFLOW depending on the minimum interatomic distance, and it was scaled. So this is our starting tolerance. Then we're going to see these P groups. So we're calculating the point group. And then it identified a particular rotation. And then here's the axis angle representation, and then the Hermann-Meguin and Schoenflies representation. So we have the point group, then P group K lattice is the reciprocal lattice version of that. So again, it's just a transformation. Then we have the F group. So again, these are the operations confined to the particular unit cell, which in this case was a standard conventional. So if you remember, it's 4 times as large as the primitive, and AFLOW is going to kind of allude to that by if you look at the bottom of the F group, you'll notice that it recognized that this cell is not primitivized because it found 4 internal translations. And that's because we're working with the conventional cell, which is 4 times as large as expected. And you'll notice it gave you the non-primitive internal translations. And so basically these are essentially the lattice point positions. So in the conventional cell, there's 4 lattice points, 1 at the origin, and then 3 on the other faces. And you can see those are given by these equations here. And again, similar to what the space group information was giving, there are 192 unique factor group operations because it's in the conventional cell. P group Xtal is a little different than the factor group because we're just removing the internal translation, or we're removing the internal translations. And so that's what we define as the P group Xtal. And then we have some point group information here, similar to what we saw in E data. We continue, then again, P group KX, so the dual of the crystallographic point group. The Patterson symmetry is in reciprocal space. Basically, it's the vector set symmetry. So again, I didn't really go into too many details, but there's some nice descriptions online. If you look up Patterson symmetry, that'll give you, there's a nice description on that. Then it tells you the symmetry in equivalent atoms. So this is similar to the Wyckoff positions. And then I mentioned A group is, let me scroll back in the slides. So this was, I think, yes, slide 11. It's when we center the origin on a particular site, on a particular atom, and we find the rotational symmetries about that point. So that's what the A group is giving us. And then at the very end, so we continue to go to A group, and then that's it. And again, information about the symmetry and equivalent atoms, or the symmetry equivalent atoms. Okay, so that was what was printed to screen. Now, if we do LS, you may have noticed that we wrote some files. These look exactly like the ones that we saw when we did AFLOW --run to do the DFT simulations. And again, for convenience, we zip them. Again, you can control what file format or compression format you want, but by default, we use XC compression. So let's go ahead and take a look at what's in this file. And again, I have it on the left as well if it gets a little difficult to read. But let's look at AFLOW. AFLOW.pgroup.out.xc. So you can see that this is the point group file. So this is the point group operations of the lattice. There are 48. And then here you can see that we give things in different representations. So this is unity. So let's actually go down to a more interesting one because the identity isn't really, it's more trivial. But we can see, okay, here we found a rotoinversion. It has this particular Hermann-Meguin and Schoenflies symbol. And on the left here, this is kind of the roadmap, if you will. Then you have this UC, which is the 3x3 rotation matrix in Cartesian coordinates, so C for Cartesian, and then also in fractional space, the corresponding 3x3 matrix. Then we have the matrix generator that I mentioned. So again, this is related to the Lie algebra. And then again, related to the Lie algebra, the SO3 coefficients. Again, the SU2 Lie group and Lie algebra are given here. So again, if you're familiar with that. We also have axis angle. So again, the axis angle representation. We have the Quaternion vector. So if you remember, that's the 4x1 vector. And then we also have the Quaternion matrix. So this is a 4x4 matrix. And then we have a Boolean indicating whether or not we have inversion symmetry. So again, if you kind of forget, I have it in the slides for you basically here. So again, I've kind of labeled it out for you here. The factor group, maybe I'll just use this instead. Maybe it's a little easier to see. You'll notice we have the same thing for the factor group, but if you remember, we include internal translations now. So now we have C tau and F tau. So these are the Cartesian internal translations and the fractional internal translations. And then there's also basis atoms map information. So basically atom mapping information. So if you remember on how we actually calculate or determine the isometry is we take the original atom position and transform it, and then compare the original and transformed atom set. And so basically this is a mapping that says, okay, these are the atom indices and these are the particular atoms that mapped onto one another. So it's kind of trivial in this example that I show here, but maybe let's go ahead and look at a nicer example. So if we do aflow.fgroup.out, and I'm going to search for froze on me a little bit. I'm going to use gedit just in case people aren't familiar with Vim. So gedit aflow.fgroup.out xc. Oh, never mind. It doesn't like compressed files. We could either unzip it, but maybe I'll just do Vim instead. So basis atoms map. So this is how you search in Vim. You just hit slash and then whatever keyword you want. And I'm going to find a more interesting one here. Okay, so in this case, this particular operation was, take a look. Okay, this was also identity, but it has a translation associated with it. So this is a translation here. And basically you can see the basis atom maps gives the index of which atoms map to one another. So the position corresponds to the atom position of the original cell, and the actual value is the index of the transformed position. So you can kind of see that the 0th atom mapped to the first, and then the first atom mapped to the 0th, etc. So basically this is a mapping telling you which atoms mapped when you transformed. So it might be a little complicated to kind of see here, but you could, if you wanted, you could kind of compare, you could actually apply the transformation to your crystal and see how the atom positions change and kind of recover this map on your own. All right, and so a lot of the other, let's do :Q. Anything that basically says P group in it is going to look just like the other P group that I showed you. The other one that I want to show you is S group. Again, it has the same information, but it just includes the lattice translations as well. And those are given here. All right, so I know there's a lot of information. And again, if you're not too familiar with crystallography, maybe you're a little overwhelmed. But again, there's a lot of information in the article, and then also readmes that'll kind of explain this in further detail. But the other thing I wanted to mention is we can run the command again. So if you go to, let me just type it again. You do aflow --aflow-sym. You can do print equals JSON and then funnel in the geometry file. It's going to do the same analysis, print the same things to the screen, but you'll notice now you have dot outs and dot JSONs, and the JSONs are just a JSON form of this. So it's going to look really messy if I open the file. So I'm not going to do that. Instead, I'm going to show you the Python example. So again, we always have a Python counterpart. Actually, sorry, I keep doing Vim. That's kind of my go-to editor. But let's do gedit example. And again, just like some of the other Symmetry Python modules, we have, again, we import all of the classes. We have the rock salt structure we're importing, and then we use this get symmetry function. And it's going to do the same analysis, and then it's going to save it to a JSON. And here in this particular script, I'm just going to print the number of operations in each group, and then I'm going to print one example factor group operation. So I'm grabbing the F group keyword, and I'm going to print the one at index 5, which corresponds to the 6th one, because we start from 0. So let's just go ahead and see what we get. On Python example. All right, so if we scroll up, we can see here's the counts. So basically we have 48 point groups, 48 in reciprocal space. Again, factor groups, we have 192. The space group, you may be wondering what this number is. So basically for the space group operations, this is to represent our entire crystal. If you remember, the space group defines the full symmetry of a periodic system. And so essentially you can go out into infinity, right? But in this case, we essentially truncate out to a particular radius, which is defined in the code, but it's also an option if you're interested. Again, if you go to the README, you can look more into that. But essentially, these are the number of space group operations out to a particular radius in your crystal. And then the last thing that I asked was I wanted it to print out one group operation. So one of the factor groups. And again, you see this key value pair relationship. So again, if you want, you can grab, I want the Quaternion matrix, and then you can grab this and integrate it into your own workflow. All right, so that may have been a lot. I know that this particular exercise, there's a lot going on, so feel free to ask questions, post in the chat or raise your hand. I'd be happy to answer questions. But the takeaway here is that for the different symmetry types of your crystal, you can calculate it with AFLOW, and you can hopefully grab some of these operations and use them in your own research. And again, there's always the online functionality. So you can, again, if you have a structure, and then if you go to the symmetry groups, you can click on this, and you can see you can calculate all of these. Here, you can actually calculate them separately online. You can also do that via the command line, but for instance, if you want the factor group, you submit. And here we had already saved the JSON, so it's a JSON form. And if you wanted to only calculate one of, maybe you just wanted the factor group instead of everything, you can do cat MGO, AFLOW, and then instead of AFLOW-SYM, if you just want the factor group, you can do F group. And it'll just calculate up to F group. And I think in this case, it's going to, you just want to be careful if you're doing multiple analyses. It'll kind of check if you already calculated something in that directory and it'll erase it. But you can see we only calculated up to F group in this case. And so one thing I want to mention is that with the AFLOW-SYM command, so if you do the -- AFLOW-SYM, again, you're using that full consistency check. So you're making sure that the factor group and the point group are consistent with one another. But if you just do factor group, you may not necessarily be consistent with the space group. Maybe there are some tolerance issues. And so I really recommend using this one to ensure that your symmetry results are consistent across all different descriptions. Okay, so that one I think was probably one of the most difficult demos. So if you have any questions, again, post in the chat. So I think we have about 35 minutes left. Yeah. Okay. All right, so that let's go ahead and go back to the exercise folder. So cd .. to go up. We do ls. So we have 3 more exercises or 3 more demos, and then we'll do the exercises. So let's go into the Crystal Spin directory. Did somebody have a question? No question, or? Okay, maybe not. If it is, oh, okay. So I do have a question, at least in the chat. Where or how is the Quaternion matrix applied? So the Quaternion matrix, we don't actually apply it really in the code itself. We just calculate it so that way you can actually use it. So basically, we're finding the symmetry operations, and then AFLOW, once it finds the symmetry operations, it'll determine the different representations. So it'll, given this operation, what is the rotation matrix, what is the axis angle, and what is the Quaternion matrix. So right now, we don't really use the Quaternion matrix internally to calculate the symmetry or anything. We could if we wanted, but really it's for the user, so they have different representations that they can work with. So again, Quaternion matrix might be useful again for computer graphics, or maybe the Quaternion vector as well. But I think the Quaternion vector is smaller, so maybe it's more, maybe it's cheaper to use. But you could use the Quaternion matrix, and that's really useful if you're kind of combining matrix multiplication. So you can do matrix vector multiplication with the 4x4 Quaternion matrix. But so yeah, hopefully that answers your question. We don't really use it for anything internally in AFLOW at the moment. We just provide it to the user. But great question. Okay. Again, feel free to post in the chat for the questions. For the next exercise, we'll be doing the crystal spin. So I had mentioned this earlier. Let me kind of resize my screens here. So the crystal spin is essentially what we're doing on slide 12. So we're introducing the magnetic moment to see if that's a degree of freedom that breaks symmetry. So let's take a look. So we kept the README. So there's kind of a bit of information here, but scroll up just a little bit. Okay. So we are going to compare the space group symmetry of the body-centered cubic chromium structure. So I've given the geometry file for you, and we're going to specify the magnetic moment. And there's going to be 2 magnetic configurations we're going to look at. So non-magnetic and then anti-ferromagnetic. And so the postcard generally only has the atom information. And I think, I don't believe there are any conventions in the postcard where you specify the magnetic information in the postcard. Typically you do it in the in card, right? If you remember. So let's go ahead and go back. So this is how you would do it via the command line. So you would use the AFLOW, and then whatever command you want. There's a few commands that are supported, and we use the magmom flag. So similar to how you would actually in the in-car, it's a similar tag magmom, and you specify the magnetic moment on each atom in your geometry file. So let's go ahead and do that. So ls, so let's go ahead and cat. First, let's see what the structure looks like. Again, somebody I think asked in one of the previous sessions, can we model magnetic structures? And this is kind of how you would do it. At least this is how you would analyze the symmetry of magnetic structures. And then again, if you wanted to actually run it in your simulation, you would specify the magnetic moment in the in-car, for instance. So you'll notice that we had to expand this to the conventional cell so we can actually specify the magnetic moment in our unit cell. Otherwise, typically, if you use the primitive cell, you can't really specify different spins because there's only one atom in this case. So to do this, we would do cat cr_bcc.postcart. Let's do the AFLOW-SG. So this is the space group. And let's first do no magnetic moment. If we do this, we get space group 229, which is like the example that I showed earlier. But now let's specify the magnetic moment. So we have two atoms, magmum equals, and I said, let's do antiferromagnetic order. So we can do spin up 1.0 and then comma negative 1.0, let's say. So this is an antiferromagnetic configuration. If you do this, the space group changed because we considered the magnetic moment. So it's a degree of freedom that broke symmetry. Alternatively, let's say you had a ferromagnetic system. So if they're both 1, you'll notice that actually we didn't break any of the symmetry compared to the original. So, and that makes sense because they're both spin up in this case. So this is collinear. You could also do non-collinear, and AFLOW will auto detect this based on the input. So let's say you had, I don't know, 1.0 and then 0, 0, and then you had, I don't know, negative 1.0, 0, 0. So again, you'll see that, again, this is another type of antiferromagnetic ordering. And let's say you mistyped and you actually only had 5. AFLOW will let you know, there's an error. You need to, it couldn't detect collinear or non-collinear, so there's something wrong with your spin input. So check your input spin. So you can do it via the command line, but also if we were working with VASP, and let's say you had the in-car, which also has the magmum information, or maybe the out-car, if you did a magnetic spin polarized calculation, then you would get the magnetic moment after the fact. So you can actually specify the path to the in-car or out-car via the magmum flag. So you can either explicitly give the magnetic moment, or you can have AFLOW read it from the in-car or out-car. I don't have any examples here, but we'll actually see, I think, in another exercise that we can do that. And so this is applicable for not only just the space group command. So if we cat the README again, you can kind of see, you can do this for the SG data, E data, Wyckoff positions, the Pearson symbol, etc. Anything that considers the atoms in the symmetry. And again, as per usual, we have the Python example. Similar thing, we use the SG data, and then we have this, we input the postcard, and then you just need to make sure that you specify the magnetic moment in the input. And again, we have a Python README that you can kind of look at to kind of see what inputs you can play with. So let me exit and just run the script. Space group 229 and 221, so no spin and with spin, the expected result. Are there any questions about the crystal spin symmetry? Again, we also have some online functionality for that. So if you go to the AFLOW-Online, you'll notice we have this magnetic structure here as well. And so in this case, it's a similar type of format. So you would do something like, let's say 1, 1, 1, -1. So in this case, there are 4 atoms. We're specifying collinear spin. And in this case, we made sure that the sulfur atoms have different spins, because originally we had space group 166 in my example. And let's make sure that we're doing, let's do space group. So instead of 166, now we get 160. So again, it kind of broke the degree of freedom, or it was a degree of freedom that broke symmetry. And again, this would also be applicable for the Wyckoff positions. And again, you'll notice, again, it's 160, but it gives you the Wyckoff positions. Okay, any questions about the crystal spin? All right. Again, feel free to post in the chat, and when it pops up, I'm happy to answer it. So I think we just have 2 more exercises or demos, sorry, and then we will do, we'll break out into some groups and we'll do just, again, some exercises just to familiarize yourself. If you have any questions, that might be a good time to ask as well. But let's go into directory 7. So 7 tolerance. And let's see what we're going to be doing here. Okay, so I mentioned that AFLOW typically will use a default tolerance value, but we also wanted to give users the degree of freedom to change the tolerance. And so you can do this by essentially appending the tolerance to the particular command of interest. So for example, you could use the default tolerance value, or you could specify, let's say, I want my tolerance threshold of 0.005 or 0.001 angstroms. And so we can do that via the command line. And just as a reminder, we have 2 preset tolerance values. So actually, if you append basically these strings to the command, as you see on the left here, so in this case, AFLOW minus AFLOW-SG equals loose, then it'll do the minimum interatomic distance divided by 10. And if you don't specify anything, then it defaults to this minimum distance divided by 100. Okay, so let's do this example. And the idea here is we want to see that if we change the tolerance value, does the symmetry change? So let's cap the postcard that I provided. Then let's do AFLOW minus AFLOW-SG. And you can append the tolerance value to the command like this. So we're going to do, first let's do tight, which is the default. So if we do this, we get space group 204. Then if we hit the up arrow and change the value to, I think I said 0.005 angstroms, let's see what we get. So we actually get space group 200 now. And if we do 001, then we get 195. So again, this is one of those systems where the crystal positions are kind of straddling certain symmetries. And so what's actually nice is if you're familiar with symmetry subgroup supergroup relationships, you'll actually note that space group 200, one of its supergroups is space group 204, and one of its subgroups is 195. So actually with this tolerance changing, you can actually capture some of this symmetry subgroup supergroup relationship. And so again, this is kind of a nice validation scheme for the AFLOW-SYM tolerance scheme. And so let's say, so I kind of provided these tolerances because I knew that the symmetry would change. But let's say you didn't necessarily know what the symmetry was going to change to, and you kind of wanted to do a range of tolerances. You can indeed do that with this command here. So it's a new feature that we recently added where you can do a tolerance scan or tolerance spectrum, like I showed in the example before, or in the introduction, basically recreating this essentially. And so this first number is the starting tolerance, the second number is the ending tolerance, and then this is the number of steps that you want to do. So let's go ahead and do this for this command. So hit up. Let's remove the tolerance and then do tolerance underscore spectrum equals. And let's go ahead and do 0.0001 and then colon, in this case, because we're kind of doing ranges. Then let's do 0.01 and let's do, I don't know, 30 iterations. And you'll notice that, okay, we have space group 195, then you can see the transition to 200 And then eventually, I don't know if we went high enough to see 204. I don't think we did. We probably should have done something a little higher, but you can do the same thing. Oh, one thing I guess I should mention is AFLOW, again, will always try to find consistent symmetry. So even for these single tolerance values, it might do the tolerance scan if it found inconsistent symmetry. So if you wanted to find places actually where it broke, then you can suppress the scan by just adding no scan. So it won't employ this corrective procedure here. So it would just throw essentially an error saying it couldn't find it. But in this case, I think it works. So again, it's the tolerance value and then the space group found at that particular tolerance value. And so you can do this for the space group command and also the Pearson command. We haven't added it yet for other commands just because the output might get a little messy if you're trying to do it for something like eData, which prints out everything. So, and then of course you can also do this with the Python module. Sorry, I always do vim, let's do gedit. And again, it's a similar procedure, open the file. We're going to do get SG data in this case, and then you specify the tolerance somehow like this. So tol equals type, and or you could use a number, and then we're printing it here. Oh. Undo. There we go. And then you can run the script. And you can see it's the same example that we did before, but just in a Python version. And again, in the slides, I kind of have a quick reference. Let me go back to here. There we go. Okay, so it looks like there was a question in the chat. How do we know the valid space group after using a tolerance range? So that's a very good question, and it doesn't really have an easy answer. In general, I guess it depends on if you know what the space group is, maybe experimentally. So if you remember in the introduction that I gave, we did a benchmark, and we found that in general, using this tight tolerance here, so this tight tolerance here, gave us good results with experiment, or it validated well with experimentally resolved symmetry. So if you have an experimental result, you can kind of easily check that. And so I think probably the best option is this epsilon tight. So it's the minimum inner atomic distance divided by 100. And we found that this is pretty good with experiment. But it is possible that maybe you have an experiment and they reported something different. I guess the hope is that with this tolerance spectrum, analysis you can do, if you don't get the space group that you expect, it could be a tolerance issue. And maybe depending on the resolution of the particular experiment, maybe I found a different space group. And so that's kind of what this tolerance scan is hoping to help mitigate is, maybe there are different tolerance values with respect to experiments. So maybe, you can kind of help to corroborate the experiment with a package like this. So it's kind of hard to say what is, the global, what is 100% the correct space group. It's kind of hard to tell. And so that's why we have these tools and options to kind of help you figure that out. So unfortunately, I can't, say for sure that, experiment and this package are always going to agree. But with these tools, I think you should be able to kind of see what's going on, because it could be a symmetry subgroup relationship like we saw here. And so that could be what the experiment is also showing. So yeah, it's a great question, but unfortunately, I can't say for sure, what is the correct space group. But great question. But I guess maybe I'll kind of take a step back, and it will at least be consistent given the atomic positions. Because the other thing you have to keep in mind is, experiments are typically looking at XRD, for instance. And what we're working with are geometry files, which are basically, given maybe an XRD, you might convert it to a coordinate file or a geometry file. And so given the atom positions that we have, I would say that AFLOW-SYM will give you the correct result based on what the input is. But yeah, I think that's a great question. So another question, in this example for 0.001, not 0001, tolerance gives same space group as tight. Is this right? So I guess you're referring to the tolerance spectrum in this case. So we did 001. Is it the same as tight in this case? I think tight gave us 204. Okay, so actually let's not do the tolerance scan. So, okay, let's do these individually. So you'll notice AFLOW-SG equals 0.0001. So that was the first one. So it gives 195. And then if you do tight, you get a different space group. And so is this right? Yes, it's consistent with the subgroup relationship. So in general, if you kind of increase, this tight tolerance is actually is larger than this guy. So to actually see what this is, one way you can do it is it's actually printed in the Y car. You'll notice here in the header file, or the title of the file, then you can see that this is the tolerance value here. So this is the default tight tolerance that was used. So it's 0.0028. So if you were to do 0.00228, then it would be equivalent essentially to doing tight. Why it's not clear? I guess I'm not sure if I understand your question exactly. Better cutoff should give same as tight. It's a smaller tolerance threshold. I don't know if you would say better cutoff, but the tolerance value is smaller. So 0.00001 is smaller than the tight tolerance cutoff, because the tight tolerance cutoff corresponds to this 0.0228. So it's a larger tolerance than this 0.0001. So I think the results are consistent in that for a tighter tolerance, you would observe lower symmetry, space group 195, while for a looser tolerance, you would observe, you might observe higher symmetry. Okay, yes, basically tolerance deals with how distorted the atoms are. Yes, that's correct. So it kind of helps to accommodate if there's distortions in the atoms' positions. That's correct, if they're not ideal. So again, yes, it goes back to this idea of the mapping that I discussed in one of the first few slides. Sorry, my PDF isn't rendering. There we go. So yes, it's to accommodate something like this. So this middle position. So again, if this tolerance is larger, then you might grab more symmetry elements or find more symmetry elements. So we observe higher symmetry. So yes, that's correct. So yeah, but no, this is a great question. I'm glad that you asked. Okay. So I think what we'll do is we have one more demo, and then I think we should have enough time to do the exercises. The exercises should be fairly straightforward, just kind of some practice. All right, so this last one we kind of already saw in the first day is the k-paths. So if we do CD8 k-path and C, so we can see that basically what we want to do is we just, again, kind of wanted to highlight this idea that you can take the particular geometry file and determine the k-path via the command line. Actually, let me go here. So the Brillouin zone. So let's go ahead and cat the postcard. So again, rock salt. And then we do AFLOW minus k-path. And so if you look at the output, you can see at the top, we have a primitive cell. And you'll notice it's the AFLOW Standard primitive cell, if you remember. And so again, this is zeros along the diagonal for FCC. And again, as Dr. Osis mentioned earlier, we kind of have this S prim versus prim. And so in this case, for the high symmetry K-paths, we typically, again, have the standard primitive cell. And from this standard primitive, then we determine the high symmetry K-paths. So somebody asked, is there an option to pass along with K-path to specify number of K points in each line? Default is 20. Actually, I don't think there is an option at the moment. Yes. So as Corey mentioned in the chat, there's a parameter in the AFLOW-RC file. Yeah, I wasn't sure. I don't think there's a command line option. We could potentially add it, but in the AFLOW-RC, yes, you can control it there. So thanks for mentioning that, Corey. So we have the standard primitive. Perfect, there's the keyword, default bands grid. And so then you can see that we have the K-path here. And so again, just kind of going back to how we come up with the standard primitive cell. Basically what we do is we have a standard definition, and that's given here on the left here. And so we basically take our lattice, we convert it into the reciprocal space by doing a dual transformation. Then we do a Minkowski, so this makes sure that the, I believe the lattice vectors are as orthogonal as possible in reciprocal space. And then we convert it back to see what the corresponding real space lattice would look like. And that's essentially how we come up with this definition of the lattice. And then from this, we've come up with 25 Bravais lattice definitions. So again, we already saw some of the Brillouin zones in the high symmetry K-paths. We've standardized this. And so you can see here are the 25 Brillouin zones. Actually, if you go to Wikipedia and search Brillouin zones, you'll actually see the Brillouin zones that were created by Professor Corderolo at Duke. So these are actually, he created this standard. And so again, you just use the K-path. And again, yeah, it looks like you can control it in the AFLOW-RC and possibly with this bands grid command that Corey mentioned in the chat. And so again, we kind of already saw this, so I won't go into too many details there, but that's how you can do the high symmetry K-paths. All right, so the last thing before we go into the exercises, maybe for a couple of minutes, is the Python module. So if we look here, so we've been using this Python script, and it was always referring to this Python module in this directory. So for those who are familiar with Python, I would encourage you, if you like the symmetry functions and you want to incorporate them into your workflow, you can take a look at what the Python module is actually doing. So basically, it's wrapping around the AFLOW executable. So the AFLOW command, it's generating the corresponding AFLOW command based on the analysis you want to do. So get eData, you can pass in some options, and then it converts everything to a JSON. So I won't go into the details here, but if you're interested, I would encourage you to look at that. And so you'll need this directory to actually use the Python module. And there's actually a command, if you do AFLOW, I believe it's AFLOW-SYM Python, then you'll notice actually from an AFLOW command, let's say I didn't give you this directory, then you can run this command and it'll create in a subdirectory in the AFLOW-SYM Python, this directory here. And from the command line, we generated, again, the AFLOW-SYM Python script, which is exactly the same that's given here. So again, after the workshop, if you didn't download this file, if you run this command, you can regenerate the Python script. All right, so with that, are there any questions about the functionality that I've shown? We have about maybe 6 minutes or so. So I would say maybe let's try and get as far as we can in the exercises. I don't know if we still want to go into breakout rooms, the rest of the AFLOW team, or if maybe we just want to have them do it here since we're low on time. But basically in the exercises directory, if you just kind of wanted to see very quickly. You can see basically a lot of the examples that we went through before, we have basically some subdirectories, and basically given here, basically we're going to calculate things like the space group, Wyckoff positions, Bravais lattice, and K-path, and then also the AFLOW-SYM command. So let's go ahead and take a few minutes. I guess let's not break out into breakout rooms just in the interest of time, but I'm going to give people maybe about maybe a couple minutes, and I encourage you to go through some of these exercises, and then maybe in the last minute or two, I'll briefly go through some of the exercises. And if people have questions, I would encourage you, we can kind of have this last 5 minutes as kind of a discussion and showing the examples. So yeah, let's take maybe about 4 minutes or so and just kind of go through the exercises. And again, please feel free to ask questions. And again, at the end, I'll try to show as many examples before the end of the time. I'm actually going to pause the recording while we're just kind of here. Okay, so are there any questions so far on the exercises? I know there isn't a lot of time left, so if you have any questions or are having any trouble, please feel free to either raise your hand, post in the chat, or even unmute yourself. I guess while I'm waiting for any questions, I'll just kind of go briefly through some of the results, and then we'll take a break. But so basically, this first example, basically the directions are here, but also in the README. So basically, I just wanted you to do the space group and Wyckoff commands on these two structures, change the tolerance, change the Wyckoff settings. So again, just as a reminder, I'll just do one. So, but we'll cat the postcard, then AFLOW minus AFLOW-SG. That does the normal space group command. If you wanted to change the tolerance, you can use, again, append the tolerance value, so maybe 0.1. Doesn't change in this case. The other thing that you can do is Wyckoff. Again, you can get the Wyckoff positions. You can change the setting. The default is setting 1, and we're specifying setting 2 now. And you'll notice that it indeed did change in this case. So we had setting 1 originally, because this was a centrosymmetric space group. Now we're setting 2. You can see that the origin changed. So we kind of saw this example already. Again, if you wanted, you could play with the tolerance spectrum command. So again, this, if you're doing the AFLOW-SG command, you did the tolerance spectrum. You could kind of see how this changes if it does. But in this case, I think I vetted this structure and I don't think it changed. You could do something like this. Yeah, it seems pretty stable at 227. So any questions about that? That was the first one. I think I'll just go through the second one. The third one was pretty self-explanatory. It's a K-path example again. And then the last one was using the AFLOW-SYM, and I'll probably show that one pretty quickly. So, and again, feel free to stop me if you have questions. I'm just kind of going through this so we can kind of see how things panned out. So in the second exercise, I basically wanted you to determine all of these attributes. You could use the separate commands if you wanted, so -- Pearson Symbol, things like that, or lattice type. But I would just recommend, again, using this edata command. So if you cat the postcard, AFLOW -- edata, that'll give you basically the answers to all of these questions. And again, of course, you can use the JSON format as well. And then we'll skip the third one because that's just a K-path one. We've done many exercises on that as well, or already. This last one was basically to do the AFLOW-SYM command and compare the lattice point group operations. And so again, just as a reminder, we cat the structure and do AFLOW minus AFLOW-SYM. And I'm actually going to put the output to a file. So again, symmetry log. And the reason I'm doing this is because I want to count the operations. So if I go into symmetry log, what the question was what is the ratio between the cardinality of the factor groups, or the counts of the factor group and the crystal point group? So again, I think I've already kind of alluded to this idea already, but basically I wanted to see how many factor group operations there were. So there are 96 factor group operations. And then how many point group operations of the crystal? 24. And so the question was, what is the ratio? So it was 96 divided by 24, right? And as you would expect, it's 4. And does this make sense? Can you rationalize this result? And again, I kind of alluded to the fact that this is the zinc blende structure, and zinc blende we know is FCC. And so we know that the ratio between the primitive and conventional cell is a factor of 4. And so this factor makes sense. All right, and so those were the exercises. Again, feel free to play with the exercises during the break. I would encourage you to do so. Are there any other questions before we break for lunch? I'll be here for a couple more minutes. So if you do end up having questions, I would encourage you to ask them during the break. One thing that I want to mention is, so we're going to take a break from 12:30 p.m. Central Time to 2 p.m. Central Time. So basically an hour and a half break. So we'll see you back at 2 p.m. Central Time. And then I'll be continuing with structure prototyping. So again, generating new structures, because we've kind of taken for granted these crystallographic structure files. And now we're actually going to see how we can generate them and also change the geometry file format, so CIF, ELK, etc. And we'll see how we can generate these in an automatic fashion.